Hey, greetings, everybody. All right, so quick introduction for me. I spent about 26 years in the Air Force across pretty much all aspects of the space life cycle, from architecture to acquisition, program office kind of stuff, into launch operations and mission operations kind of stuff. After that, after retirement, about 5 years ago, I came to aerospace. First 4 years were spent with DSG, where I work space enterprise architecture activities with headquarters aft space. After that, about a year ago now, I moved over to ETG as we stood up the Digital Engineering Integration Office. I'll talk a little bit more about that later in this course. That's where I'm at right now, focusing on ecosystem development for aerospace. Education-wise, undergrad was doubly on to eventually a PhD in systems engineering. All right, let's switch to the course itself and do a quick overview of what we're going to talk about today and the rules of engagement. So this course is really intended to provide a pretty decent overview of digital engineering, including what it is, how we're using it across the community, and what benefits we're expecting to see both within aerospace and the broader space enterprise. And it's really meant to address this gap that we've noticed in the overall curriculum. There's a lot of stuff out there, model-based systems engineering, a lot of M&S stuff, both in aerospace and externally, but there really isn't a good overview course of digital engineering and what it is and how it brings these things together. So this is meant to address that. And you guys are part of the first offering of this, and maybe the only. We're going to record this, and the intent is to share it with others. There may be a subsequent version of this that we present at GSAW as well, but this could be the one and only one, so you're part of a special group. In terms of how long you're going to be here today, the intent is that we're probably going to go about 3.5 hours. That includes a couple 10-minute breaks, if that gives you an idea. In terms of content, we're right around 3 hours here. And who this course is aimed for is really anybody in aerospace, technical or non-technical even, who just want to learn more about digital engineering. You hear this all the time. Is it just a buzzword? What does it really mean? Let's help people understand that. Students ideally would have a good familiarity with systems engineering and modeling and simulation, but that's by no means required. Just a lot of the examples and discussions are going to be anchored to those kind of ideas. So if you're familiar with that, that'll help. And then ideally as well, everyone would have taken the Digital Fluency Overview course prior to this. If you haven't done that, I highly recommend it. This was made available last fiscal year and explains a lot of the basic concepts of digital transformation. It touches on digital engineering, but also things like artificial intelligence, machine learning, different capability development, CI/CD kind of stuff, modern infrastructure. So it's a really good overview course that's about an hour in length. In terms of the rules of engagement for today, discussion is absolutely encouraged. Either voice, come off mute, feel free to weigh in that way, or chat if you prefer. There's really no need to have your camera on. That's up to you. Maybe even is better from a bandwidth perspective not to. Feel free to ask questions in the chat at any time. I have the ability to see chat. It's up on my screen, so I'll be monitoring that probably at the end of each slide. Also, feel free to ask questions. Come off mute at any of the prompts. I'll probably stop every few slides or so and just ask any questions or comments here. So it gives you an opportunity if you prefer to go that route. Either way, there are going to be a lot of opportunities for engagement across this course. I'm definitely going to need your contributions. There's poll questions, there's slide builds that ask you to weigh in. So please help me with that so there aren't those really uncomfortable long silences. One more slide just on the course itself in terms of the learning objectives, kind of why you're here, what we want you to get out of this course. Number one, be able to identify and describe these core components of model-based systems engineering. This course isn't about model-based systems engineering, but we really start there because it's an important foundation of digital engineering, and it's important to understand how it's different from traditional systems engineering. Then we'll talk about the core components of digital engineering, and then really the relationship between these two things. In what ways are model-based systems engineering and digital engineering alike, and in what ways are they different? Be able to list the key benefits, model-based systems engineering and digital engineering. That's another key objective. And we'll also dive into some of these key concepts you see associated with digital engineering. And we'll talk about those in detail and how they relate. Want you to be able to cite specific examples of model-based systems engineering and digital engineering, and then list challenges associated with overall digital transformation. We'll talk about the benefits and the good, but we also want to be candid here and talk about some of the downsides and challenges related to digital transformation. And then we'll switch gears to more what's happening at Aerospace with our digital transformation. What's our strategy? What's our approach to start making this happen and adopt digital engineering across the company? And we'll want you to be able to talk about, or at least be familiar with the 5 lines of effort that Aerospace has established for its digital transformation. And last objective is just to be able to find other sources to continue your learning if you want to dive in deeper into these areas. All right. In terms of an agenda for today, I have each of these 6 topics, or 7 if you count the course intro that we just completed, that has these key questions here. Why? What are you doing here? How long are you going to be here? Who am I? What are we going to talk about? What are you going to get out of this? Hopefully we covered that sufficiently and we can put a check mark there. The next sections, we're going to start with model-based systems engineering. Not a whole lot of depth here, but at least get everybody level set to what is a model? What is simulation? What is model-based systems engineering, and why is it potentially a big deal? And then we'll do the same thing with digital engineering, which is more the heart of why we're here. And what is the relationship between model-based systems engineering and digital engineering and the benefits of these things? Then after the break, we'll move into some of these concepts and terms you hear a lot associated with digital engineering. What is an ASOT, this authoritative source of truth? What is a digital twin? What does it mean to be data-centric? What is the digital engineering ecosystem, and what is that comprised of? What is a digital thread? So those are things we're going to focus on in section 3. In section 4, what I call digital engineering beyond the basics, let's tie some of these big concepts together and let's take a step back in the bigger picture. How are digital engineering and modeling and sim related? What's happening across the community in terms of digital engineering today? There's a lot going on, but a lot more that we need to figure out. What are the biggest challenges and how does it all fit together? And after another break, we'll go to what's happening at Aerospace with digital engineering, what our strategy is and how we're implementing it. And then a short summary at the end to just wrap everything up. All right, let's go. Section 1, model-based systems engineering. So the key questions here, as I mentioned in the agenda, we're going to cover what is a model, what is a simulation. We're not going to go into a lot of depth on modeling because that's really not what this course is about by any means. But modeling is foundational to the topic of digital engineering. We're going to talk about this connection in a lot more depth later. But for now, I just want to briefly introduce the idea of modeling sim, get us all on the same page. And the same thing largely goes for MBSE. I'm going to spend a little more time there, but that's not what this course is about. But really, if anybody who's had any background in DE knows, to really understand what DE is, you got to understand where it's coming from and some of the core components like model-based systems engineering. So we're going to start there. You're not going to be a practitioner of model-based systems engineering from this course by any means, but it's important to understand the relationship between the two and that they're not the same thing. You see a lot of cases where people just say MBSE/DE because it's a shortcut, but we're going to talk about the differences as well. All right, here's the first opportunity for you guys to engage. And I want to put up a poll question here. And just get a sense of how everybody feels about models. Like, do you feel like you're really familiar, kind of familiar? Okay, that's probably good, Melissa. We can post that. So does everybody see those on the screen, the results?
Yep.
Okay, so nobody's saying they're not familiar with models at all. That's great. Somewhat familiar, very familiar. Okay, good. That's kind of what I would expect, a good breakdown in those kind of areas. If I'm going to put up a list of definitions here, and I am, in fact, going to put up several definitions. What kinds of things do you think those definitions are going to say? What keywords are going to come out of this? Again, you come off mute or put it in the chat, whichever. What are some key aspects of what makes something a model? For any of you who are somewhat familiar, very familiar, should be straightforward. Models have to have a purpose. That's good. Thank you. Capture view of reality, repeatable, digital prototype, simplified representation of a real system. That's good. That comes up a lot. Predictive representation. Great. Yeah, I see representation a lot, and that's probably the word you see in most definitions. Let's go ahead and go to the next build here. So here are definitions from DoD, also some non-DoD definitions. And these first three, you see this again and again: representation, a selective representation, a simplified representation. And then it goes on to say things like, it does have to have a purpose. It addresses a specific set of concerns, or it helps promote understanding. This is why we model. We want a representation of something. And that's an important part of this. But there's also the idea of a simulation, which is really most simply regarded as a model, but a model over time. There's this time component to it. It's executable in some sense. And then any discussion of models has to include, I think, by law, some reference to George Box's famous description of models, and all models are wrong, some are useful. But that gets this idea that they need to have a clear purpose. We recognize they are not the same thing as the entity to which they're meant to represent. We deliberately do abstract things, but we do it in a way that allows us to still allow for some purpose that is important to us in terms of decision-making, analysis, or whatever. So basic idea of a model. Key takeaways here: the idea, we've got representation of reality. It's an important shortcut to save resources, facilitate understanding, and it should be fit for purpose. All things that we capture in those definitions. This slide shows some examples of models, or maybe potential examples of models. I just kind of glancing through this. Do you see anything there that maybe you would think isn't a model? There's up in the left, there's a SysML representation of requirements. Bottom left, it's an HVAC sort of depiction of a building and airflows. The big one, the colorful one in the middle, is a CFD, computational fluid dynamics representation. What do you guys think in terms of model? Okay, so someone said Sharpie is real, so maybe not a model. Yeah, I have a hard time thinking of the Sharpie as a model. That's only what kind of stands out, right? That's a little different. But it depends, right? So I've got a Sharpie here. Maybe I want to, camera's over here, but maybe I want to explain to a colleague what happens during a launch, and how the launch vehicle is oriented, and what happens at separation and engine cutoff, and how, what happens to these. I could use this to be a model to actually communicate some kind of information to someone. So it all depends on how you use things. Maybe even the Sharpie is a model, but it certainly is a stretch here. And maybe that animation of the train set, that's a model of real trains. It's a simulation because it's moving, and it can help gain additional understanding of that world. But a key point here for our purposes is I want to differentiate between physical models and abstract models. And I see a comment in here: a descriptive analytical representation. That's good. Like a computer is a tool rather than a model. I like that. For our purposes, in terms of digital engineering and digital models and the benefits we derive from that, we're going to be focused on the abstract models. So not things like the Sharpie, not the car, not even this architecture set, this model of some building. We want something that's logical, it's mathematical in nature, digitizable, and that gives us a certain set of benefits we just can't get from things like the Sharpie. It doesn't lend itself to this integrated analysis. Any comments or questions at this point? All right, let's do a quick summary of benefits and challenges of modeling. So models have these obvious benefits of being able to, by adopting a more structured representation of something, using formalized modeling tools and languages, we typically have to confront and resolve any ambiguity in the way we think about the item we're trying to model, and for similar reasons. The actual content of the model and the nomenclature we use has to be consistent when we adopt the formalization of modeling it. Other benefits of modeling are that it enables us to do other really useful things like interrogate the model in ways that help us answer questions or conduct analysis involving various things we care about, particularly if they're modeled in a compatible manner. And again, the Sharpie doesn't do that kind of thing for us. We can't really interrogate the Sharpie in a meaningful way. Modeling also inherently provides really good configuration management, allowing us to track and record and share how things are changing or maybe not changing over time. But all of these benefits you see on the left, they do tend to come with some downsides you see on the right.
Aaron?
Yeah.
Sorry. So this is Justin Langlois out of Vandenberg. What we're talking about right now is a model that we are taking a model that is already in production or a model that has already been generated. What about when we're trying to develop a model that isn't clear cut? So in that case, reduces ambiguity of representation. But if you don't capture representation correctly, you don't really reduce the ambiguity. And a lot of that will go into what assumptions you put into the model in trying to put into that representation. So how do you overcome? I understand it for like a train set, or I understand it for, something that's already established. But in a lot of the things that we're trying to do here at Vandenberg, we're taking it to that next level. We're trying to understand space C2 and what does that mean? And we're trying to do it through digital engineering and MBSE. But we're not representing, we don't have a good model representation because our assumptions are horrible.
A model of the model. Yeah.
Right, exactly. So how do you kind of overcome that, if you don't mind?
I don't have a good answer for you, Justin. That kind of actually gets to some of these challenges, and I'll brave the key takeaways. Good modeling can be powerful, but it requires expertise, investment, discipline, and what I didn't add there, what you've brought up, you have to have some understanding of what you're trying to model, at least to get started. Now, this can be iterative, and you can model and then play it off against the real thing and see if it was useful. But to model something, you have to have some sense, I think, of what it is you're trying to model. So I think you're getting into a deeper question of modeling than I can really get into today for this course.
Yeah, fair. Thank you.
That's a great question. One of the reasons I wanted to hit modeling right at the outset here, though, is because it is so fundamental to what aerospace does in terms of our value proposition to the customer. Modeling and simulation analysis are just core components of our business model. No pun intended. All right. That was really it for modeling. Again, I'm not going in depth on that. I just wanted to be on the same page regarding what it is I'm talking about modeling, and it's the digital side, not the abstract stuff. So next slide. What is model-based systems engineering? Here's another poll just to get a sense of where you guys are at right now in terms of comfort level with this term. If you bring that up, Melissa, be the same question as before, but now for MBSE. How familiar are you? Okay, that's good. Thanks everybody for responding. Got 30 responses there. This time definitely was skewed more toward the less familiar. Only 5 people felt they were very familiar. Lots in that middle branch are somewhat familiar, even a few not familiar at all, as opposed to when we did the model question. So that's helpful to see that. Let's do the same thing we did with the definitions of model, though. I've got a couple I'm going to put up here because the definition of MBSE is pretty standard, maybe even more standard than the definition of systems engineering is these days. But when I put up these definitions, what kind of words do you think are going to pop up here? What themes and terms do you expect to see in these definitions of model-based systems engineering? You can put them in chat or offer them out loud, whichever you prefer. Okay, some ideas: digital environment, system representation, integrated information sources, maybe things about the functions that need to be done, drawing a distinction between document-based systems engineering and model-based systems engineering. Yeah, that's a key part of model-based. Yeah, what about about the scope of it in terms of you think in terms of acquisition? Is it just parts of, oh, thank you. Life cycle. That's exactly what I was wondering if somebody would put down. That's good. All right, let me go ahead and show these definitions. So the two we've got here, one from Nkosi from pretty long time ago, 2007. I mean, the idea of MBSE has been around at least since then. They were talking about in academic circles even prior to that. So we're getting close to 20 years of talking about model-based systems engineering. And then there's a more recent one out of CBOC. But you see these themes of, okay, I'm doing systems engineering. I'm doing requirements design, analysis, verification, validation throughout the life cycle. But I'm doing it in a modeling way. I'm applying modeling to the kinds of systems engineering things I do. You see that same theme in both these definitions. So key takeaways are, one, most of the community at this point just references or refers to the Nkosi definition of MBSE. You'll sometimes see the CBOC one or a couple others, but the Nkosi one's pretty good, pretty standard. You'll see that all the time. And fundamentally, just at the basic level, you want to understand model-based systems engineering. Well, if you understand systems engineering, it's doing systems engineering in a modeling way. Modeling plus systems engineering equals model-based systems engineering. And like one person put in the chat, it's really this difference between doing things model-based versus product-based. We're going to talk about that a little more in the next couple of slides. It's applicable to all those things that you do in the systems engineering lifecycle, requirements, design, technical planning, configuration management, test, and V&V. The scope of MBSE, though, as you'll see in both of these definitions, it's about systems. It's usually a system. And there's nothing that necessarily precludes MBSE from being beyond a system, but typically you see MBSE applied at the system level, and you hear it talked about it at that kind of level of scope. And like I mentioned, the terminology has been around for a while, maybe a couple of decades now, but the concept of doing engineering in a model-based fashion has been around a long time. I mean, 50, 60 years easily in some of these domains with CAD things going back into the 60s. So you can think of model-based systems engineering as being a subset of model-based engineering, but it's just late to the game. It's something that we began to practice with a little more rigor in the last 10, 20 years. We're still learning how to do model-based systems engineering because all the other engineering domains have a big head start on this. So that's really in a nutshell what model-based systems engineering is from a definition perspective. Let's talk about a little bit the way it's changed things, or at least has the potential to do so. So if you look at this page, you see down at the bottom another depiction of the V. If you're talking about systems engineering, you're always going to see some sort of V depiction. Here it is, but there's some big question mark in the middle where I have legacy systems engineering products. So think of this as the old way of doing things, and that's probably not even accurate. It's the current way of doing things for a lot of programs and a lot of places. Well, what kinds of products do you typically see, or would you expect to see that middle section where the question mark is that brings together these things? If you were talking about a traceability matrix, what format is that in? Or the requirements document, what is that? ICD, yeah, it's a specific type of requirement. My question for you guys is, what format would that ICD be in? How would I pull it up and look at it? Yeah, Excel, one way, PDF, yeah. When we get really advanced, we put things in PDF because they're locked down at that point. Word, exactly. Good. So it's these types of products that are static. The Microsoft Office kind of suite of products for PDF or a web page or something. Generally, these things tend to be very static. And so we have all of this knowledge that's manually captured in a disparate collection of static products. And the integration between these products is hard. It occurs mostly in the minds of the stakeholders here and the consumers of the information. And that representation tends to be very stovepiped. It's natural language kind of representations. We write up the requirements in Word with a lot of flowery language around it. And even when we get to the requirements, there can be a whole lot of misunderstanding and ambiguity in how those requirements are interpreted. And so this all hampers consistency and understanding across the community. And fundamentally, with all these different pieces that are static and aren't connected in any meaningful way, as the content evolves for each one, this requirements document and this test plan, they're updated at different rates and they're not kept in sync at all. So that's a huge challenge that I think all of us have lived in the systems engineering community. Scooter, what table of contents is not good enough? Yeah, I guess that's one way around it. Let's look at the more integrated version of this, the model-based approach to systems engineering. So the same V, but now there's something else in the middle. What takes the place of that question mark in this diagram if we're not going to have those static products? A database, it absolutely could. Yeah, but you think even simpler in terms of what we're talking about here. Single information source. You guys are overthinking. You're doing great. Don't say web page, Scooter. What would be at the center of model-based systems engineering? Yay, models. That's all I'm looking for here. And you guys are right that a database could inform that and be part of that. And the idea that it's a single information source is right as well. But at the center, where you're trying to actually connect all of this, are the system models. And then out of that, you absolutely can build the artifacts you need. You can extract them on an as-needed basis in a more human-readable format or some convenient way because somebody else can't read the model, or maybe it's delivery to the government. There's a way to extract from the model, but fundamentally, you do your work in the model. That's where knowledge and information exchange occurs in MBSE. And so by replacing these simpler static products with integrated digital system models, the content is much more able to maintain synchronization. And this is absolutely critical to managing the complexity we see with systems today that are growing increasingly complex. We have all these challenges with knowledge exchange. We want to go faster. The idea is that MBSE can help with this. And again, the traditional products that may be more suitable for some circumstances can still be extracted and used as needed. All right, I'm going to do another pause here for any questions or comments before we go into a couple more specific examples of model-based systems engineering. Key question at this point: what is the breadth of model types that comprise typical integrated system models? For model-based systems engineering, which is obviously a subset of model-based engineering, it's going to be potentially anything that we're doing in the systems engineering community. For example, simulations aren't typically utilized, right? Absolutely. They are, but probably not so much in MBSE. So that's a good point. They end up feeding other people's simulation and deeper analysis. And then those boundaries get a little bit fuzzy between, I want to have my risk model that model-based systems engineering is maintaining, but maybe I want to simulate what would happen if certain aspects of these risks are realized, or maybe it feeds another analysis that tells me what the risks are. So it's still got to be connected to some deeper simulation potentially. But I think you're right. Not a lot of simulation in MBSE. Why are SE slow to adopt model-based engineering? I think the impression model-based systems engineering came first, then MV. Oh, that's really interesting. Yeah, model-based systems engineering, it's almost a philosophical question about why it was so late. But I think one obvious answer is systems engineering was later. Now, we started doing some basic systems engineering in the 60s and 70s with NASA and DoD stuff. But the full up adoption of systems engineering probably wasn't late, probably was a decade or two behind the traditional disciplines of EE, aero, and mechanical. So maybe there was part of that. Maybe systems engineers are more resistant to change. I don't know. If anybody has any thoughts here as to why that might be, I think it'd be interesting to hear them. Either you can come off mute or put them in the chat. But we were definitely very late to the game. Like I said, it was more like early 2000s before the idea really started to take root. All right. Let's go to this idea of how systems engineering relates to model-based engineering. So this might get to a little bit more to those questions about where does simulation come in, and it probably won't help us with the question of why MBSE was late to the game, but at least maybe better illustrate the connection between the two. I'm going to use an example from the Digital Fluency course. If you have taken that, you'll recognize this. I think it illustrates really effectively where the process how it comes together in terms of building a house. So model-based engineering introduces various elements of the house to include things like how the foundations can be constructed, how it will be wired for electricity, how the cabinets will be built and placed. Model-based systems engineering seeks to bring all this together, accounting for factors like all the relevant requirements that the user has, the buyer, the neighborhood, even the bank, the best timing of the construction based on weather and availability of subcontractors and the actual sequencing of these activities. And so we don't build the walls before adding plumbing and electrical. You got to do things in a certain order. Your schedule is really important. So all this helps to ensure the culmination of these efforts is the house that the buyer wanted, or DoD speak, it's the system that the COCOM wanted, or the user needs. All this is made easier and more efficient if we can virtually see everything laid out and figure out the kinks as early in the process as possible, which is what modeling can do for us. So just a warning, I'm going to expand on this house example as we go along, anchor a lot of other key concepts to the idea of building a house. I think this is a fairly concrete, intuitive example of building something and how it needs to come together. Just looking at the chat, Scooter's comment about system engineers driven by adherence to process. The process didn't change. Yeah. One other thing on MBSC I want to hit on briefly is this idea of the 4 pillars of MBSC and our modeling language. This is the most depth I'm going to go into on MBSC in terms of practitioner kind of stuff, because that isn't what this class is again. I just want to show you the basic framework of MBSC, because you will see this a lot and it may come into play in some of the later discussions we have today. So these 4 pillars of MBSC are structure, behavior, requirements, and parametrics. And so we have diagrams that correspond to these things. We have structure diagrams that help us understand how the system is used. We can document that. We have behavior diagrams that show how things come together and sequences and the operational piece of things. We have requirements, because what is system engineering without requirements? We have to track how all these things relate, whether they're being satisfied. And then parametrics, we're answering questions like how much, how well. This can inform that quantitative analysis and is a key touch point for other modeling domains. I mentioned we'll talk just real briefly about language. This is all I'm going to say about model-based systems engineering language. One of the typical, and it's just one of, not the only, but one of the most commonly used languages you'll see for modeling in MBSE is SysML, System Modeling Language. And it's a graphical language. You can see an example from earlier in that upper left where we just showed requirements diagrams, just blocks that are connected and show relationships. And these are meant to span these 4 pillars I just talked about. It is a language still, so it's got a standardized structure and syntactical construct that has to be adhered to, that helps communication and understanding between different people who interact with the model. It's not dependent on any tool or methodology. SysML is separate from that. And it grew out of UML, the software language, but it's been tailored to focus on the needs of systems engineering. So any questions on kind of a little bit more of the details of MBSE before I move into some examples and how MBSE is really related to legacy? All right, let's do this. If you think of this continuum of legacy systems engineering on the left side and model-based systems engineering on the right, and we're trying to move toward more model-based approaches. And you think about the types of things we do in a systems engineering world, what kinds of things do you think would show up on the left side, more on the left side of this continuum? CAD. I don't know how often systems engineers are using CAD. And if we are, I would think that would be more on the right side. You're modeling something. CDDs, some spaces, a lot less than defense space. Documents. Yeah, lots of documents like we talked about earlier. Architecture diagrams. It depends on how we depict them, whether they're more on the left or more on the right. Again, same thing with the development documents, or or CDDs or ICDs. Maybe it depends on how we depict them, where they show up. Requirement trees. Yeah, I'm thinking of the ones that end up in PowerPoint. But if you're using doors, probably more on the right side. So the kinds of things that I put down as potential examples for left side, more legacy side things is that SRD is captured in a Word document. And it's static, and that's what we're sending around. And people make changes to that, and it's hard to track. And we're highlighting things. You've got to search within Word to find stuff. Maybe we're creating risk matrices manually. In fact, I know we still are doing this. You see these in PowerPoint all the time, that you've got the 5x5, and people are putting in a particular item, particular cell. That's how we communicate levels of risk to the decision maker. Maybe these design reviews that are such a key part of the systems engineering lifecycle for development of a capability, they're really just PowerPoint. It's hundreds and hundreds of slides of PowerPoint and multi-day fun. I imagine a lot of folks on the line have lived through that. Maybe we're exchanging contracting information via static docs. And that's pretty standard for a long time now, that we send a Word document package or PDF to the contractor. They send Seadrills back as PDFs or something along those lines. So what might that look like more in the future? Well, imagine these things more in modeling space. Instead of that requirement in a static Word document, we're using a tool that can help us really understand and manage those requirements. Something like Doors Next Generation, which can readily show the relationship between all of these layers of requirements and quickly identify if there are orphans or some connection that needs to be made or some open issue. Lots of tools for doing that. Same thing for risk management. Lots of tools can help us do that better than the PowerPoint. We can capture requirements in a modeling language like SysML I just talked about. Maybe we can receive our Seadrills, our contract deliverables, as actual models, and that they can integrate into other models from other contractors with the government and quickly inform decision making rather than have all these transformations between the imperfect static documents. Maybe we can communicate status with one another via dashboards, or we can do our design in Cameo. Maybe the design reviews could actually be more model-based, and it isn't death by PowerPoint. In fact, let's talk about that a little bit more in terms of what design reviews look like, how they are different in a legacy world and an MBSE world. And so a legacy design review, and I'm talking about things here for SRR, SFR, PDR, CDR, we traditionally have those products that are very static. They're locked down. We have folks review them over a long period of time, and they're relevant to this system only. There's a big burden on the system, the subject matter experts, to review these artifacts. And it tends to be a lot of just reading through lengthy representations of something. Pretty challenging to manage the complexity of these systems and understand all the interdependencies when you have all these disparate artifacts that are just essentially flat files of information. And so there's a lot of preparation here that tends to precede this very long multi-day PowerPoint driven event. What a model-based design review might look like, and I say might because we haven't seen a lot of instances of these. I'll talk a little bit later about where digital engineering is happening across the community, and there have been several beginnings of a digital design review or model-based to some extent. But what it really looks like, we're still trying to figure out. But the kinds of things that might be here is those artifacts are model-based, that we're actually reviewing content within the model and understanding those connections within the model. And those connections much more readily may extend beyond the system of record. So the PDR may be focused entirely on one system, but we're already bringing in, because we have these connections readily available, what's happening with other systems because they have important implications to our development. What's happening with the ground system, what's happening with the launch vehicle, and being able to more readily understand those implications between the interfaces. Structured models shared across stakeholders, across disciplines. That would be great if that was happening across all of the engineering disciplines, not just within model-based systems, not within systems engineering. The idea is that these tools can help us with the tedious parts of the process. They can help us identify where the problems are. We can focus our brain power on the harder, bigger problems, but use these tools to identify escapes and problems more readily than people are good at doing. We can reuse these models much more easily. We can revise them as needed to help reduce the burden on the subject matter experts. And then maybe that months of preparation is still there to some extent, but it's not death by PowerPoint, it's death by models, but it's going to require a different type of presentation with different tools in a different environment and with different expertise of the people that are there in order to interpret all that. And Scooter, continuous decision-making versus epoch-based decision-making. Yeah, that's a really good one that I actually put into the next phase of this. I'm going to show this slide again a little bit later when we talk about digital engineering. And I think what you just described there is probably more where we need to go. But everyone needs to know how to view the same model. Well, they need to communicate in the same language. There is a burden on everyone to have new modeling skills and interpretation, at least, of those. But they don't need to be the same model and an understanding of how to navigate that model. Yeah. So there are downsides to transition to modeling, and we'll talk about some of those challenges. You guys are already hitting on some. That's good. Okay, I'm going to hit one more slide on model-based systems engineering, and then I'll open it up for any other discussion. And this one is just what the expected benefits are of model-based systems engineering. And we've hit on these one way or another up to this point. We want to identify problems sooner, more easily, provide confidence that we have closure, that all the requirements are coming together. The system is going to be delivered as needed. And you can get that bigger picture and more confidence through this integration of models. We can improve the concurrency of lifecycle processes, what's happening between one phase of development and another phase of acquisition, as well as better connections between the engineering disciplines, because they are more comfortable and have been using models for a lot longer. So let's get those connections in place. Enables and enforces clear communications of needs. And primarily this relates to requirements and understanding that whole traceability, but also other things like contract deliverables and how those relate. MBSE promises to increase both the efficiency and the effectiveness of development. This idea that you have models that can be reused, tweaked, you're not starting from scratch. Same idea as taking somebody else's template in Word and using it somewhere else, but a lot more standardized. You can facilitate management of complexity. Get this idea of more informed decision making, that we understand the implications of changes and how those things are interdependent. So earlier we talked about a requirements document that's just in Word, and requirements change. How do we capture all of the implications of that change? It has implications to design, cost, schedule, at least potentially all of these things. The more that we can capture these interdependencies in modeling space, the more agile we can be in responding to the inevitable changes that occur during development. So that concludes the section on model-based systems engineering. Let me open it up to any questions or comments here. See, speaking of changes, is there some type of version control for MBSE systems like Git for code bases? Within a given tool, I'm aware of that, but I'm not aware of something that broadly does that. If anybody else does, feel free to weigh in there in the chat. James says, in order to fully implement what you're talking about, we'd have to get suppliers and sub-tier suppliers on board. Using the RL10 as an example, at least 3 of the critical suppliers to the engine manufacturer will not share drawings, or in some cases, even ERBs, even with the manufacturer, let alone aerospace and US government. Fantastic input, James. When I talk later about the challenges, and you already have addressed one of the big ones, is this idea of digital engineering, for it to realize its potential, does require a greater degree of collaboration and willingness to share across entities. And there are cultural reasons why this is hard, not to mention even legal and data protection kind of things as well, but that's a big challenge to all this. have the same issue with a satellite bus. I'm not sure what you meant there, Anthony. You just mean in terms of data sharing? See, Cameo's Teamwork Cloud has version control. Yep. Roll back. Yeah, with any given tool, I'm aware of some good ways to do that, but not across tools. Anthony, you say yes. Yeah, okay, for the satellite bus. Yeah, lots of different subs there who aren't real happy to share their pieces of it in order for an integrated model to make sense. All right. Anything else before we move on to actual digital engineering, the reason why we're here? Let's see one more comment from Kyle. I would image a custom plugin, or maybe that was Imagine. I would imagine a custom plugin would have to be made to do version control across tools. Maybe. In general, the tools are another pretty big challenge with MBSE and digital engineering more broadly in terms of cost, compatibility, interoperability of data and exchanges. And there are a few what we call orchestration type tools that aim to do this that are beginning to try to plug these holes across the tools. But again, I'm not aware personally of how they do the CM piece. All right, let's go to section 2, digital engineering, the basics. Here we're going to talk about what is digital engineering and then the relationship between what we just talked about, model-based systems engineering and DE, how they're the same, how they are different, and then the benefits of DE, which in some ways absolutely do overlap with MBSE, but they go broader. So let's do another one of these definition reveals and poll questions, this time related to digital engineering. How you guys how do you feel about digital engineering in terms of your familiarity? Okay, that's probably good. We've got a good group of responses. It looks like it's broken down pretty similar to how MBSE was, but actually maybe skewed a little bit more toward the familiar side, which would surprise me because I would have thought MBSE would be a little more familiar to folks. But either way, there's kind of that big group in the middle, somewhat familiar. Presumably you wouldn't be here if you totally knew things, but at the very familiar, you guys, I'm counting on you to tell me what kinds of things I'm going to see in these definitions I'm about to reveal. So I've got 6 different definitions of digital engineering. What kinds of terms and themes do you expect to see here? And really, anybody can respond. I'll look at some of the latest chat while you guys are doing that. Sounds like interoperability and ability to share model outputs without sharing the models themselves, the key current challenge. Yes. Okay, so some of the words coming in for potential definitions for digital engineering. Digital twins may be mentioned. Yep. A common ontology that allows us to communicate across all these disciplines. That's good. The model tools, BCSs. I don't know what that means, Scooter. BCSs aren't as mature as a Git or subversion or the underlying formats. Okay, back to the CM kind of topic. Version control system. Okay, thanks. What other keywords might we see or themes or topics when somebody talks about the definition of digital engineering? Somebody a colleague were to tell you, hey, this is what digital engineering is. What terms do you think they throw around? Whether you understood what they meant or not. Digital thread, that's another one you're going to see come up. That's good. It's another one I was thinking you guys would throw at me because you've actually mentioned it earlier a little bit. See, multidisciplinary digital floor plans. Yeah, especially when we talk about a house. System engineering V. The V doesn't come up explicitly, but certainly the idea of doing life cycle stuff. Yep, good. ASA, there it is. Thank you, Aaron. I was hoping somebody would mention that one because that's fundamental to almost every definition. Let's go ahead and reveal these. So you've got here 6 different definitions just from the DoD side. I've got a second page of definitions from non-DoD sources. And you see these themes of, all right, well, digital engineering, digital, you see that word a lot, integrated, Authoritative sources. You see that in the DoD Digital Engineering Strategy from 2018, which we're going to reference repeatedly throughout the rest of the session here. This is really kind of the foundational document for a lot of this thinking that started to permeate the DoD and what digital engineering could be. You see references to data and models. So that's really important. It's not just models, it's also this underlying data. And then lifecycle activities. So yeah, systems engineering kind of stuff. So that's all kind of, you see those highlighted in the upper left. The definition right below that, Defense Acquisition University, it uses almost exactly the same definition, but it has one slight change, which is potentially interesting. You see, instead of system data and models, their published version of the definition is the plural systems data and models. And that's potentially really important because the scope of DE does tend to go beyond an individual system. And I think that's I have to speculate why they made that change, but I have to believe that's why they did that. You have the Navy Marine Corps definition, again, with integrated authoritative sources. Again, this reference to data and models. Again, life cycle. But you also see now this computation-based approach. We'll talk a little bit about what that might mean. Over at the Office of Undersecretary of Defense, some of their digital engineering stuff, they say, hey, this is a new and groundbreaking way to do things. Whereas model-based system engineering is just doing the same thing the other engineering disciplines have been doing for decades. Maybe this is something totally different. Updates traditional systems engineering. This one's kind of backs off a little bit. It's just doing systems engineering in a new way. But again, there's this reference to computational technology. And then the bottom right is a little bit larger excerpt from the Space Force Vision for a Digital Service, which came out last year. They talk about authoritative sources of truth. They talk about some of these other things you guys put in the chat, not just big data, but there was a mention of digital thread. Somebody mentioned digital twin, but that hasn't come up on this page. We'll see on the next page, I think. And this linkage back to model-based systems engineering and modeling and simulation, that those are key parts of what constitute digital engineering or help empower it. Let's go to the next page of definitions, and these are non-DoD sources. And the first one I'm going to show there on the upper left, or I want to draw your attention to, is what I'm going to say is a bad definition. And it's from a course that is done by a private company for the DoD. And they have their definition of digital engineering, in parentheses, it's also known as model-based systems engineering, or, model-based engineering or model-based systems engineering. I just wanted to show that to highlight that's an outlier. And I think this kind of definition is what helps cause confusion in the community. Digital engineering and model-based systems engineering are not the same thing. And hopefully by the end of this section, that'll be clearer. But this is the kind of thing you'll see in certain places that can add to confusion. So my recommendation would be to disregard that, but know that there are cases where you'll see that sort of representation. For CBOX, mentioning body of knowledge, you'll see this reference again to computer readable models and life cycle stuff. You guys see definitions from Boeing. Down at the digital engineering group, they have a reference to digital twins, the idea that this is for system of systems, again, not just a single system. BAE talks about cultural. I definitely want to highlight as we go forward. We've already talked about that a little bit just in terms of data sharing, but cultural is a big part of what makes digital engineering different. And then another reference here to digital thread down for Lockheed Martin. So just to kind of get a sense of, there's a lot of different perceptions of what digital engineering is. And so Christopher Deloy says, so there isn't any real agreement on DEs. Perfect. I'm glad that you said that, because that's a really good segue into this slide about the key takeaways. The first thing I noted as well is these definitions of digital engineering lack consensus. There's probably a reasonable amount of consistency across DoD, probably less so across DoD. That's how I read those. And then that definition from the DoD Digital Engineering Strategy document from 2018 is the most referenced in general, just so that you know that one's probably the closest to being authoritative. Emphasis, though, that you do see. So let me just talk about some themes that I think are fair to extract from that group of definitions. It does tend to be this idea that it's not just the models, like we talk about with model-based systems engineering. This idea, it's the data as well, the underlying data. Earlier, someone mentioned that what was in the center of that MBSE box when we showed the V for a model-based approach wasn't just the integrated models, but the data underlying that. That's really where you start talking about more about digital engineering. And that may be another opportunity for exchange and interoperability that doesn't exist at the model layer, and why this could potentially be so important. And that also means this idea of an ASOT, the authoritative source of truth that you go to, that's probably at the data layer, is really central. We also see this theme of being integrated across disciplines. And it's not just systems engineering anymore. It's all these engineering disciplines and maybe broader. So this idea that maybe it's not just all the engineering domains, maybe it's not just science kind of stuff and physics models, but maybe it's even bigger. So if you look at these questions to ponder, is DE just updates to traditional systems engineering, like one of the pieces I pulled from the Office of Under Secretary of Defense, or is it new and groundbreaking and innovating how we build, which was some other definitions? What degree of revolution versus evolution are we talking about here? And then what are these disciplines that we're trying to tie together with digital engineering? Is it just technical because it is called digital engineering, or perhaps it's even bigger and gets into business processes and costing and contracts, things that aren't typically thought of as engineering type things? Okay, let me kind of glance at the chat. I've been paying close attention there. See, not a good start for designing a single course. Yeah, part of the challenge here. But I want you guys to understand where there is consensus and clear understanding across the community and where there isn't. Because DE is a new thing, and there are some things that we understand and agree on, and there are things that are still being debated. So I want to make sure that that's clear as we go through this. ASOT requires significant configuration management processes. Very astute observation. Yeah, we'll talk about that when we dive into ASOTs and some of the challenges. But ASOTs should be just as relevant to traditional SE processes. Why are they so key unique to DE that they're almost definitional? That's a really good question. So I think it goes to the fact that it's the data layer. So it's one thing to say, I'm going to use models to do my work. It's another thing to say that we all agree that we are going to use the same underlying data to populate those models. And that starts to get to an ability to integrate across a broader spectrum than we otherwise could. And so maybe you could argue MBSE should have always thought that way, or any sort of model-based approach, but DE makes that linkage much more explicit. Is DE a subset of digital transformation, or are the two being used interchangeably? That may be something where I get sloppy sometimes, but strictly speaking, digital engineering would be part of a larger transformation. I think at Aerospace in particular, we're using the two terms pretty interchangeably. We're going to adopt digital engineering. That's going to represent the core of our digital transformation. But if you really start to tease that apart, there are other pieces that we need to do that may not be digital engineering. And it goes back to this last question on this chart, questions to ponder. If we start making changes to our business processes and policy and how we're organized as part of our transformation, is that digital engineering change, or is it really something bigger? And what term do we give to that? And Anthony, your comment there I see about the opinion statement, let's integrate the technical disciplines first and worry about others later, is exactly the approach that the Digital Engineering Integration Office has taken. We are focused on the technical side first. So it's interesting you said that. We agree. Okay, let's do the slide of MBSE versus DE. So I've made the argument they're not the same thing. I hope that you guys buy that. Here's why they're not the same thing. You know, just looking at the definitions, but also what you see in terms of how the concepts are being applied across the community. Clearly, they're related, but both model-based system engineering and model-based engineering are a subset of DE. So just like MBSE is a subset of MBE, MBE is a subset of this larger idea of digital engineering. So whereas MBSE is focused on models, DE tends to be focused on models and data. MBSE is going to support the traditional system engineering activities we see, but DE is going to incorporate those models and connect them with the other engineering disciplines. And it may, again, incorporate these other data sources or other models from non-engineering parts of capability development. Maybe even, I didn't mention operations. The idea that we are in operations, we're getting operational data, that can be part of a digital engineering construct. But there's this piece that we've poked at a little bit, and then you guys have asked good questions that get to this. Why haven't we doing this sooner? Why is there so much lack of consistency in the definitions? Well, you saw with MBSE, maybe 15, 20 years old now, we've got consensus on the definition of what it is. Digital engineering is a pretty new idea. You saw it was, the dream maybe was discussed and envisioned 5, 10 years ago to start bringing these things together, but you didn't even see a formal definition until about 5 years ago out of the DoD at least. And we're still trying to figure out what the implications of a digital engineering approach would be and how we would achieve them. So there is some squishiness here. I would argue that MBSE is more of an evolution from SE, and that digital engineering really represents a state change into something else. And basically the scope of what we're talking about is going to vary by the application domain, but I think in general, in the 5 years since the DoD came out with that definition, it's gone beyond their original conception. That because we're learning more, we have innovative practices, technology's increasing, cloud has really taken over, the cloud technologies and the ability to do things that we didn't even think were possible 5 years ago or nobody thought of. These are changing what we actually think digital engineering can do. And so by definition, what it is and how we're describing it is also changing. AI/ML has definitely advanced a lot in the last 5 years. Yeah, it's a real thing in everyday development these days. Okay. Here's another opportunity for you guys to engage and need your help to fill in the right side of this table. So on the left, I've got these different elements: purpose, benefits, scope, applicability, and so on. And there's MBSE filled in. Here's the purpose of MBSE: improve efficiency and quality. We talked about that. Enhance communication and collaboration, improve decision making. And then, at least to some extent, there's this ability to manage complexity and maybe start to integrate across the enterprise. What would you expect to see on the right side here for digital engineering? I'm going to reveal this block. Same things, different. I'm just going to do the top block now, purpose and benefits. But you're right, Anthony, on scope, you've already got it right. For models and data will be the difference on the DE side. What about just purpose and benefits? Link data to MBSE. Keep going on that one. I'm not sure what you mean as the purpose. Ensure the same configuration is evaluated for all analyses conducted. Applicability, enterprise. Yeah, you guys have jumped ahead and you're doing great. Great data across multiple disciplines beyond just engineering. Yeah. ASOT and the interoperability piece of it. D can be more enterprise focused. Yeah, in terms of applicability. That's good. I'm going to reveal this first one on purpose because it's really largely the same. With the same arguments in terms of efficiency, effectiveness, quality, decision-making. Maybe it's just a matter of degree, especially with the collaboration and the broader scope that we're going to talk about next. But those items I have in parentheticals, the ability to manage complexity and integrating across the enterprise, really come out as key aspects of why we do digital engineering, because it inherently does involve more domains. We want to look across more systems. We acknowledge that no system exists in isolation, and we have to have a mechanism for managing the complexity of these systems of systems in enterprise. And DE is more of a means to do that. At least it's intended to be. In terms of scope, you guys got that right too. Models and data exchanges, this idea of being data-centric. This idea it's not just systems engineering, but all engineering, and maybe even beyond engineering, that we need to rethink the definition and scope of digital engineering. In terms of applicability, talked about it's not just systems and programs, but could go beyond that. What about maturity? So a couple of decades in MBSE. About how old is this idea of digital engineering, at least formally? Yeah, 2018. So we're talking about 5 years. It's pretty recent. So I think it's reasonable that we have some growing pains in figuring out what this is. I mean, for that matter, we have growing pains with MBSE. We have lots of things still to figure out there. And then how big of a deal? Rather than a natural evolution, what I'm seeing here as where we're trying to go and the kinds of capabilities that are already being fielded in digital engineering represents much more of a transformational change in the way we do capability development. And we're still trying to figure out what that means, but it can fundamentally change how we go about the processes and what we do today, and to rethink almost everything about our development processes. So let me give you an example going back to, I warned you, the house stuff. So I used this from MBSE earlier and kind of showed the relationship between model-based systems engineering and model-based engineering. Let's ratchet things up a level and see what this might look like as a full digital engineering concept. So imagine that all the stakeholders for the construction of this house, the framers, the plumbers, the electricians, the architects, and of course the buyers, the user, they all worked from the same synchronized sheet of music. And I don't just mean a set of drawings or even digital drawings, but the underlying data from which those drawings could be derived. And this data could be used not just to create tailored artifacts, but could be used to make sure that anyone involved had access to the latest truth, and that this truth could be understood. It can be communicated and visualized at any time from a variety of different software tools. And just as importantly, this data-centric representation would lend itself to analysis. It would helping us answer questions and inform decision-making about the process. What is the exact progress of the building right now? How do we compare actual costs to expected costs? What are the ripple effects if a change is made, a requirement is made, or the inspection is delayed by a week, or the contractor is sick and doesn't show up on time? How do we understand those implications? And this trade space is going to be informed by dynamic connections to external systems, not just the house, but these other factors that allow us to really see the bigger picture, like changes in the weather, what's happening in terms of the forecast and tendencies with climate in this area, a potential work stoppage, changes in commodity prices, and so on. So all of this can be coordinated a lot more broadly if everything is connected, certainly across all the builders' activities, but perhaps even across multiple builders if they're talking to each other, an entire development community pulling in and orchestrating and maybe optimizing approvals from the city council, coordinating with public utilities, transportation, construction, even the local school district. The idea is a digital engineering approach to home building might really change the nature of the process that is predominant today. Maybe more is done in parallel across construction sites, entirely different sites, to optimize key resources, scheduling. Maybe there are automated workflows that tell contractors automatically of their responsibilities and make requests to those public offices at exactly the right time, so we don't have any delays. Imagine the home inspections could occur based on an evolving digital model rather than the actual house, allowing the inspection to occur not just earlier in the process, but at a higher level of fidelity than ever before, because they can see things that just aren't possible later in the process. Perhaps the homes are smart, in a different way, and that they're instrumented in a manner that allows the builder to know, even after it's been sold, that there's a problem with some part of the house and can alert the builder even before the homeowner knows that there's a problem. That kind of idea is really the premise of digital engineering. Let's see, and Justin says, would you say link architectures are DE? I'm not sure I understand the question, Justin. Link architectures?
Things like link 16, link 11.
Oh, I'm tracking now.
Link 22. Because we say the thought is that this all started in 2018, but if link architectures fall under that DE definition, that started in 1980. And
yeah.
So
this dream of, okay, so I'm going to editorialize here a little bit, Justin. You way back, what do you think? I think this idea of integrating across, like what I just described with this house, and now try to imagine what that would look like in the space domain or DoD more broadly. I think this idea has been in place for decades. We want to do it, with the link architectures, or we've had a lot of different attempts at essentially joint command and control across all of DoD, and these have been really, really challenging. But this idea that everything is connected has been discussed for a long time. What may be different right now is that the technologies are starting to catch up with the vision.
But it goes back to, I asked a question earlier regarding data standards. Does DE drive us to specific data standards? Because right now, I would say we are in county option. It means everybody gets to develop their own data standard, and then we try to find an API to link them together. But does true DE really start to drive us to very specific standards, which seems to be the thing that everyone wants to stay away from? Is I want to be able to do whatever I want to do, and then we'll figure out how to link those together. But if we true DE, we have to have some type of standards that we're going to work towards, and that's going to be the baseline. So I mean, that's the other part of the DE equation I'm looking at is we can't, to do this effectively and efficiently, we got to get away from county option and get into, okay, these are the three options we're going to use. These are the three standards we're going to use.
I believe that the idea of standards, and what I'm going to talk to as data-centric, is absolutely central to realizing digital engineering. And yeah, that implies that there are established standards and there's a method of governance to enforce those. Otherwise, you don't have a way to exchange information at the data layer. You'll constantly be chasing different standards. Now, there's ways to, I'm kind of using the term broadly. There can be other ways to achieve that through like self-description at the data layer, that technically you're not conforming to a standard, but you're at least adopting certain tagging practices that allow for things to, like the note here, Rosetta Stone type stuff, that you can at least translate as necessary. That's a great point. We'll talk about that a little more, Justin. Thanks. All right, anything else before I move on to the last slide of, a few more slides of digital engineering. This one is, I wanted to show you guys kind of the same idea of the house, but maybe applied to the space domain or a satellite specifically. I don't think it's hard to see how these principles apply, but I just wanted to walk through it and see if this made sense. Here's how this could look for building capability. So today we routinely create models for various satellite subsystems. But what if these models could talk to each other as part of a fully integrated satellite model? And let's imagine these subcontractors are willing to share the data. And let's imagine there's interoperability that enables these models to communicate. That this model, what if it steadily matured because it incorporates everything else? So we've got this integrated satellite model here, all these pieces, and now it matures over time. It's incorporating updates to all the other constituent and relevant models. Not just the design model and components of the satellite itself, but what's happening with the requirement. Kind of the upper side are more the systems engineering and business stuff, architecture, design, risk, schedule, cost. Down below, you've got things like the environment, the space environment, the types of things we would do for thermal vac and threats. What do those models look like? And how does our system potentially respond to those? And how does that trade space look relative to requirements, cost, and schedule? And maybe we want to account for the loads analysis of the launch vehicle or overall reliability, survivability type things. All these models are relevant to what we want to do in terms of the capability, but they're completely disconnected today. Digital engineering is the idea that these would be connected. We would eventually build the system, or maybe a constellation of satellites. And then we want to, oops, I'm going the wrong way. And then we want to, it's in operations. There's a whole bunch more we want to do with modeling. We've got these other models in terms of behavior of our systems and their systems, in other words, blue systems and red systems, the physics of the environment and how things can interact, and all the other systems that the satellite constellation has to interact with in terms of ground and comms and other satellites, and the people that are interacting. All these things can potentially be modeled. And we can do things like war gaming. We can do an integrated test. We can train operators. But what's really potentially transformational here is what I just described doesn't have to wait until operations. We can do this much sooner. We can do it before the satellite constellation is built and deployed. So this is going to get into these ideas of digital thread, digital twin, we'll be talking about in the next section. But being able to do all those things in the upper right box sooner and with greater fidelity is one of the great potentials that we're talking about with digital engineering. Get over to the chat and see what I missed. Problem I see with the Rosetta Stone approach is that each tool model can be responsible for translating between an ever-growing list of other data formats. How do you maintain that? We'll talk a little bit more about that in the data-centric section. That is a good point about the challenge there, though. Yeah. Any questions or comments on this slide before I move on to another one of these continuum slides between the old way and the new way? All right, I'm going to go to this slide. Instead of legacy and MBSE, though, let's switch it out to model-based systems engineering on the left and digital engineering on the right. And let me show the next build of, this is the same stuff that was there before on the MBSE side, the idea of doing a lot of these systems engineering functions using tools, using models that can make the process a little more streamlined, effective. What do you guys think would be on the right side now? After everything we talked about with digital engineering, what might that look like on the right side? Total integration. Yeah. And one depiction of what that, one description of that is this idea of a digital thread. So we'll see that. Anything else come to mind? You know, instead of a model-based design review, maybe it's a little more beyond that. Digital twins, yep. Whole life cycle, including mission data, good. All right, here's some things that I put on here that I think could be where DE goes. You know, we've got this idea of ASOTs, authoritative sources of truth, maintaining those, making sure they're accessible, visible, people can use those, work from the common sheet of music. This idea of a digital design review. We'll talk a little bit more about what that might look like coming up. All these pieces we talked about, requirements, risk, design, decision, they're all connected as part of this larger thread across the life cycle. Digital twin can be part of this. Again, we'll talk about what that really means. But another really important part of this, I don't think anybody mentioned, but you probably intuitively get, is in order to do this, there's the idea of a digital ecosystem that makes this possible. I mean, this idea of being digitally connected across all these components is really hard to envision with the types of IT infrastructure and environments and platforms we have today. We just all deal on a daily basis with so many challenges with information exchange that there's a strong implication here that we have to have a more robust ecosystem that facilitates this. So we're going to talk about what digital ecosystem does, but that's a key part of a change between MBSE and DE. And then there's this other question I've kind of poked out a little bit, and it's maybe left as an exercise for you to ponder. Is MBSE to DE really a continuum? Maybe there is a discontinuity here whereas MBSE is really just using models to do systems engineering, and thus it's a sort of natural progression. DE represents more of a state change. It's a change of kind. We may be able to integrate our efforts in an unprecedented fashion and do capability development in completely revolutionary ways. And so maybe it's not really a continuum. Just checking the chat, whole life cycle, a massive rocket model combining models of all smaller system subs. Yeah, that's a good example too. Mission data used to revise models. That is an interesting point that gets to a key aspect of what makes something a digital twin. So we'll talk about that as well. Thanks, Anthony. Earlier, I showed what a digital review, or I talked about what reviews might look like, both legacy and MBSE. Well, let's add in digital engineering here as well, what a design review might look like. And Scooter talked about this a little bit. And what this really looks like is a little bit of an artifact of imagination, because for the most part, we haven't achieved this. But the idea would be we're presenting artifact, there are no traditional product artifacts anymore. It's entirely model-based, and we're referencing source data that we all agree is the truth. We're having dynamic information exchanges on these things such that we're not looking at an artifact that was baselined a month ago. We have the latest version showing right now up on the screen, visualized based on what is happening at that exact moment, because we're not worried about the translation anymore. In theory, we're far more integrated. We have this larger scope across an enterprise, maybe some non-engineering factors. Maybe this idea of a system design review isn't as relevant. It becomes capability reviews or enterprise reviews. And the idea that maybe their milestones might be less applicable, this idea of PDR, CDR, and so on, that maybe it's a continuous sort of activity, and there are just certain checkpoints and sign-offs based on that. And as you guys noted earlier when we talked about this, regardless of whether we're talking model-based or digital, there's going to have to be some fundamental changes in the expertise of the people participating. They're going to have to understand how to build this stuff, how to understand and interpret this, and there has to be this improved infrastructure and different processes, whether it's an ecosystem and whether we actually make changes to acquisition, 5,000 series kinds of stuff because of this. These are all potential implications out of digital engineering. Yeah, look at the chat. Helen, you may have said that even before I did. That's good. Not formal milestones, much as continuous updates. The digital ecosystem capabilities can enable this. Yep. All right, let's move to why is DE important? And then we'll have just one review slide, and that'll be the end of this section, just focus on digital engineering, and then we're going to dive in a little more depth to some of these terms. But in terms of why DE is important, let me just review the kinds of things we've already hit on it. This idea of complexity, both the system level and the enterprise. A lot of the traditional methods we're using just cannot keep up with this. We can't connect all these different pieces. And of course, what's happening in space domain, or has happened over the last 10 plus years, the recognition it's a warfighting domain just makes this all the more critical, and trying to get our hands around all of the threats in this environment. So that drives the need for additional speed and agility, make sure we're staying ahead of the adversary. And that means that through digital engineering, potentially we have this real-time access to authoritative sources of data, and everybody agrees what those are. We can accelerate the decision-making across the life cycle, the system, or again, maybe broader capability or enterprise. In terms of efficiency, we can have process workflows, we can improve productivity, have people focused on their specialty. A SME spends more time actually doing the analysis than trying to locate the data and get the right tools for it. It's there as part of an effective ecosystem. There's this idea we can deliver digital twins to operations before the physical artifact, or at least have them available for training and ConOps and development of TTPs, tactics, techniques, and procedures that can inform warfighting. It allows insight into future alternatives to better optimize across the life cycle, understanding these trades and all the connections across all the different facets of capability development. Then in terms of improved effectiveness, this idea of knowledge management is so fundamental, and ASOTs and collaboration across all the stakeholders, having data-driven decision-making and doing it at the right level is part of this. And then improving control over the evolution of system designs. This idea that we have a lot of different baselines to manage, and understanding the interplay between them is critical to delivering and maintaining a robust capability. So any questions to this point? I'm going to hit chat, but feel free to come off mute if you've got any questions or comments. We've got one more slide in this section.
Yeah, a quick comment or thoughts on the potential discontinuity between MBSE and DE.
Okay.
And one of the, it's not, this comment isn't so much a discontinuity of scope, but more of a discontinuity of kind. So for example, getting into the notion of operational analyses and even digital twins, it's not clear that the language, literally the language utilized in MDSE, is actually up to the task of actually allowing that level of particularly higher fidelity modeling of how your system interacts with the world, et cetera, et cetera. And from a physics mod and sim background, some of the conversations we've been having with the DE side of the house in terms of this whole M&S modernization, I think sometimes we're talking completely different languages, and it's not clear that the concepts and structures flowing out of systems engineering in the MBSE, and even getting into what digital engineering is trying to talk about, necessarily is currently captures the full scope of concepts and abilities that will be needed to flesh out this future vision that you have down on this slide. That's all. I think you're on mute.
Yeah. Did you want me to respond to that, or I just want to make that point because it was a good one?
No, it's a point for discussion. It's
Okay.
it's a
Let me open it up to
based
others.
on burgeoning interactions as
Yeah.
opposed to a, this is absolute reality.
Yeah. Let me open it up to the group. I think your point about whether MBSE is up to that task is very valid. That was Chris, right?
Yes. Sorry, it takes a minute to find the mute.
Yeah,
button.
I understand. Does anybody else want to respond to Chris? Brad, anything to that?
Yeah, this is Steve Lutton. What comes across my mind is that's why it's so important to talk about the interoperability and interaction between the digital engineering tools and processes and the modeling and simulation, both analytical and numerical approaches. It's that. I think, Aaron, you mentioned at the very beginning of our course that idea of being able to have the digital engineering, the model-based system engineering, and then further into the digital engineering information, models, and data, and that at some point answers to what a particular subsystem can do, whether it fits with, provides the performance within a certain parameter range, has to reach out to a more higher fidelity model and simulate something and come back with an answer. And that really creates that ecosystem that we referred to. Over.
Exactly. Yeah, so I think I also hinted that toward the end, we'll talk a little bit more advanced things like, what is this connection between digital engineering and M&S? And, spoiler alert, we at Aerospace view it very tightly and what we call two sides of the same coin. And so in order to meet that value proposition of providing these fundamental decision informing, analytically based pieces of information to our customers, we've got to make sure the two are working in concert. No easy task, though. All right.
Aaron, I was just this is Justin down at Vandenberg again.
Hey, Justin.
What this has highlighted to me, especially on the Space C2 side of the house, and where Aerospace brings value to the customer, is we need to do model-based systems engineering is really building a prototype and then building prototypes of prototypes. And that's where the digital engineering comes into play of how do I get those multiple prototypes working together. On the Space C2 side of the house, we have yet to develop the prototype. We were just going right into development of something. and don't know what that something is. And because we don't have the models built, we can't do the digital engineering to see how they interact. And therefore, that's where we're breaking down on the Space C2 side of the house. It's JMS did a better job of building the models, but they failed to build the digital engineering that goes along with that model-based systems engineering in order to ensure that there is interoperability and integration. And so that's where we're falling into the same trap here with Space C2. And we're getting fixated on specific problem areas and not on the holistic. So this course and we're an hour and a half in, and I've gotten so much out of it just from that perspective of taking it back and saying, okay, we may need to relook at how we're doing our business right now because we're not in line with what we should be doing. So thank you.
That goes back to your question from earlier of how do you model something without an idea of what that something is, right?
Exactly. But if you don't model it, you're not going to get there, right? If you don't prototype it and start to look at it, you can't get from here to there.
Unless by sheer dumb luck.
Yeah, and we haven't been that dumb.
All right. I'm going to go to this slide, which is where I need you guys' help again with another kind of interactive reveal of these concepts we've talked to at this point. And then I think right after this is the break. So if you're able to power through this, you got a 10-minute reward. These are the ideas that we talked about at this point. We talked briefly about model, MBSE, digital engineering, how MBSE and DE are like, how they're different, and then why D is important. What kinds of things are going to be on the right side here for each of these? Let's start with model. A model is like, what is the simple, easy, anybody can understand, most anybody can understand definition of a model? How would you describe that? You can put them in text or put them in chat if you like. Representation, yeah, that came up a lot. That's good. It's gonna be a representation abstraction or something. Oops, I didn't mean to go back a slide. Good. What was the other? There's another key takeaway from the definition of model. Approximate but useful, or yeah, the useful idea, the fit for purpose. So representation, MBSE. What would be a short one sentence clear definition of that? Integrated system model is a big part of it. Representation of the SE lifecycle. Yeah, support all those pieces. Yeah, so you guys got the modeling part. It's really doing SE kind of stuff. The only other thing I added in my short definition was it is a type of model-based engineering. You know, that's something that's been around for a while. A lot of people understand and get what model-based engineering is. Well, it's modeling for systems engineering activities. All right, so the same thing for digital engineering now. I just a few more words here, a little bit longer sentence, but what kind of things you think are most important to remember about digital engineering? Focus on the model and the data. Good. I actually have that in the subsequent point, but it's exactly right. Data centric. Good. Use of ecosystem across the whole life cycle. Yeah, so some of these broader perspectives. What I had is it's an integrated approach to overall capability development. It uses model-based system engineering and model-based engineering, but it's broader in its scope and tying those things together. Okay, can someone give me an example of how MBSE and digital engineering are alike? Yep, both share modeling of the system. They're very reliant on use of models. Yeah, versus artifacts or static products. And they're both looking to connect those models. That's a key part of it. The other thing I had here is they're both lifecycle focused. Right? So I've got that reliance on the models, very focused on the entire life cycle. So that's ways in which they're alike. What about different? And I'm actually going to have you guys take credit for answers you already provided. There was a lot of discussion about data centricity, using data and models. This point about broader. So I have all that plus the idea of maybe it is more of a discontinuity. There is a revolution here as opposed to, we're doing system engineering in a modeling fashion. We may be talking about changing the way we do capability development. And we are still figuring that out. Why is it important? What are some of the reasons we talked about here for why DE is potentially important? What are the benefits? Yeah, interoperability, integration, faster, cheaper, maybe better. Yeah, maybe. Less busy work. That's a good one. I emphasize that enough, but that's one of the arguments for decision agility. Great. So reveal this, the improved efficiency, the improved effectiveness, the ability to manage complexity. This is such a wicked problem. And I mean that in the technical, like engineering sense, that there are wicked problems here that we have to figure out. And digital engineering may be the means to do this. In fact, it's the only feasible hypothesis I've heard in the last several years that can get after this management of complexity. More informed, agile decision-making. I would note that nowhere on this list did I include cost savings. There may or may not be cost savings, and the data is far from clear, but the arguments for DE generally are much better anchored to these types of things, that this is the only way you can manage complexity across an enterprise is to take this sort of approach, and it's going to cost what it's going to cost, and there are going to be some significant investments. Yeah, and then Justin asked, upfront cost savings or savings over time? No question that upfront transition, it's more. And I'll talk about this in a number of respects coming up about what a transformation looks like and what those non-recurring investments are. Yes, there is more because you can't just automatically switch. And so there's this period of time where you're spending more. The question of long-term, whether there's savings, is where there's some debate, whether there's a direct return on investment. Again, there's nothing quantifiable, but that doesn't mean it's not the right thing to do. And the example I would use here for any of the folks on the line who are familiar with some of the systems engineering history, systems engineering was deemed value added for multiple decades before there was any quantitative data to show it had cost savings. The same may end up being true for digital engineering. Okay, so that concludes the first three sections, 0, 1, and 2. We've touched on that. We did the intro. We touched on MBSE and then digital engineering, the basics. Let's do a 10-minute break here and we'll pick things up with some more in-depth treatment of some key DE concepts. Next up, we're going to move into these key digital engineering concepts and what I'm calling beyond the basics. We make some of those linkages between digital engineering, M&S, and what's going on today in reality with digital engineering. Try to give you some more concrete examples. All right, so section 3, these key concepts, these are the 5 I'm going to talk about next. We're going to go into a fair amount of depth on each one, like a few slides, talk about what it is, whether there is consensus on the concept or not, where there isn't, how they relate. I'm going to show that as well, and then what the challenges are related to each of these things. We've got ASOTs, digital twins, the idea of data-centric, the digital engineering ecosystem, and a digital thread. Before I reveal the definitions, let me ask that same question. What kinds of concepts, terms, and words do you expect are going to pop up on these definitions? I'm going to show you 4 that are probably the 4 best across the community from different sources. 3 are from DoD, 1's from the OMG Object Management Group. Justin, we are talking data truth, correct? Yeah, essentially. With some nuances. It's really some help here with some words that might show up. So maybe truth, agreement on a single source. Yeah, some agreement and concurrence. But let me ask that, who has to agree in order for it to be considered an authoritative source of truth? Standards. Yeah, that could be part of this. Stakeholder community has to agree to it. Yeah. Some particular community who has an interest in it. The one who's accepting the risk, potentially. Enough people. I like that especially in quotes, because there's some uncertainty about who the people are and how many constitutes enough. Is it really an authoritative source of truth? All right, let me show you these definitions. So we've got the one from the DoD Digital Engineering Strategy. It defines an ASOT. We've got one from the US Space Force Vision for Digital Service. There's something from OMG, and then there's something actually from the Aerospace Learning Center. And I think a moment ago I characterized as the best. I'm going to change that to most prominent, because one of these is not like the other and it's not great. I'll talk about why. But in the upper left, you've got this idea of central reference. That this is the one place you go to. This is what you reference when you want to do something. It consists of models and data. That authoritative source of truth can be models and data. The next one down from the Space Force says single definitive source. You guys latched onto that correctly. It says for a given piece of information, and that all consumers of that information reference it. Okay, that sounds pretty good. The one in the upper right is the one that is potentially problematic, and I understand is being revised for those reasons. But it describes ASOT as an entity, such as a person, governing body, or system that applies expert judgment and rules to proclaim an artifact is valid. So it kind of flips the idea of an ASOT to the thing that is relied upon, to the people who are determining that it is to be relied upon. They are applying expert judgment. And that's out of family with the rest of the definitions and what you typically hear about an authoritative source of truth. So it's at least knowing that it's there, but hopefully that's being revised, because I think that causes confusion. And then the aerospace one is data or information. Members of a particular community of interest agree this is the right source to use. So in terms of key takeaways here, what I think we could conclude is there aren't a lot of authoritative definitions of ASOT, and there isn't total consensus here. In fact, sometimes you'll hear different terms for the exact same idea, or at least what is probably meant to be the same idea, the single source of truth, an SSOT, single point of truth, or even system of record, SOR is sometimes used to communicate this idea. Fundamentally, though, what you see as a theme here is this idea of trust, that some particular group has agreed to accept and endorse this source of information as the most authoritative one. And there's this idea that an ASOT is an ASOT because it is fit for purpose for that community, that enough, quote unquote, enough people agree that it's the right one. And it's totally reasonable. And in fact, will often happen that different communities may have different ASOTs for the same basic data type. You know, whether, let's say it's a threat database, one particular community may use this threat database, and another one uses a different, and that's fine. They have different ASOTs, they have different purposes, and that's part of the tapestry here. It isn't limited to information, data, or models in theory. Any of these could be an ASOT. Now, this does bring up the question of whether a person could be an ASOT. Probably they are in the strictest sense. There's information inside someone's head, and it's only in that person's head, and people go to that person when they want to know about something, and it hasn't been digitized. But that's the problem. It doesn't do us a lot of good as part of a digital engineering implementation if we can't effectively integrate that person's knowledge into our ecosystem. So maybe there's an argument that a person isn't an ASOT, but we have to recognize that even though an ASOT ideally is digitized for this federation, that's a lot to ask for all these potential data sources, especially at first as we're trying to transition into a digital engineering construct. We have today lots of people and lots of documents that are going to have a role in the near term. So we probably have to account for that in our conception of ASOT as well. So returning to the example of the house, the ASOT there could be the official house plans that get recorded at the county clerk's office. And that's what the contractors know to go reference when they go do work at the home, is they pull that. That's the ASOT that everybody agrees to for that community. Question in the chat, does ASOT refer to data itself or data formats and standards? I have only seen it, and I believe it's most correctly applied to the data itself or the models or the information they represent. This, when you start talking about the format of the data and the standards, you get into the data centricity discussion, which is relevant because you want to be able to exchange this data in an interoperable fashion. But the ASOT itself, I don't believe includes that concept. Justin's comment, ASOT is part of my concern with UDL because UDL is not ASOT, and right now it doesn't highlight the ASOT within the UDL. I will nod and agree. Nothing to add there. So why is ASOT such a big deal? Why do this term keep coming up? Why is it especially coming up as part of digital engineering? Well, I mentioned I was going to reference the DoD digital engineering strategy multiple times throughout. Here's another one of those cases. You can see this list of 5 goals here. This is just a screenshot. And ASOT was recognized early on as being central to DE. It's called out explicitly here as goal number 2 in the strategy. And it's important because it's central to effective reuse. It's central to this idea of trust. It enables the recreation of models and a genuine lineage, a tracking, a pedigree of decisions deriving from various data sources. How did you create that? Show me your analysis and show me that you can recreate it and what basis you arrived at that so that somebody else can prove out the same thing. It also serves, in theory, at least, to break down these stovepipes. We already talked about how that's almost certainly a major challenge related to digital engineering. The more that we can agree on the common sources of truth and start there, well, that fosters a common understanding. Basically, everybody in a given community knows where to start and they agree on where to start. Can you provide a concrete real-world example of an ASOT? So how about news? This could be fun, right? I'll bet most everybody on the line who follows or is interested in news or politics or whatever your particular interest is, when you go online, you have specific sources you go to and trust. Different media sources, different social media sites that you get your information from. And that's what you trust. Now, not everybody's going to agree on that ASOT, but for your community, your particular interest, that's where you go to learn. The Onion. Yeah, that's a good source. Now, the chances that we all agree on the same sources are very small, but that brings to light an important aspect and challenge of ASOT is you're not going to get full agreement on the most trusted sources across a diverse community.
So can I offer an example?
Yeah, please.
And it's from the operational world. So Link 16 is considered an authoritative source. There are issues with Link 16, but if you're in a theater of war, so if you're over in CENTCOM or you're in EUCOM right now, everyone accepts that Link 16 is the official link picture for everybody that's going to be conducting operations. It's where people are making decisions and things like that. The information may be actually erroneous in Link 16, and we may make a decision based off erroneous information, but we all make that decision together rather than, oh, well, I had different decision or I had different information, things like that. And then the other one is, yeah, GPS is another example. So, but I mean, I always go back to Link 16 because it was, started in the 80s and actually works pretty well as we go forward, and it overcame a lot of issues, especially on the digital engineering side that we are still trying to overcome now. So,
yeah, another maybe more work relevant example for folks, and I'll talk about this a little later, is the data and models catalog at Aerospace. It's undergone a lot of updates, and it's being curated right now for determination of what is an ASOT, that we actually have a certification process on what things will be ASOT, why, how you access them, what data it constitutes, and a lot of other key parameters that will influence that determination. But that's an example that's available to all of us right now. Let's talk about challenges. You guys have already hit on some of these, and I think we'll probably intuitively get them. I mean, the notion of an ASOT is pretty straightforward. Those are the benefits. We're all working from the same sheet of music. We're interpreting facts, and we're recommending courses of action to leadership. That can be hard enough when we all agree on the facts. It's pretty much impossible if we don't have the same starting point. So there's a lot of value in having that same starting point, but there are a lot of challenges to an ASOT when you start to peel the onion on how we actually achieve this. I was going to ask you guys to like think through it, but you guys have already put a lot of good examples in the chat. So I'm just going to capture these and maybe add on a little bit more. One is establishing an ASOT can be hard. Like, who decides whether some particular data set is truly an ASOT, and what happens when you have different people who have different opinions? How to resolve that conflict? Should we even certify? I just talked about maybe doing that for some certain data and model sets. Should we do it, and how do we do it? What are the criteria, and how do you apply them consistently in a way that is meaningful for users to understand the implications of something being certified as an ASOT? There are a lot of challenges with sustaining an ASOT. Who actually owns a given data set, especially when it may be comprised of data from different sources, but then somebody congregates that into something else. Who pays to maintain it? There is work to curate and keep it current and accessible and useful. There's cost to that. Who can actually make changes to this data set? What is the process for doing so? How do we curate it? How do we keep it relevant? What does the actual life cycle of an ASOT look like, from the stand-up challenges to the sustainment to actually decisions to deprecate it, potentially, that it's no longer the right ASOT or it's been supplanted by something else? And what do we do about versioning and keeping track of all the changes? The whole CMing of an ASOT can be a challenge, especially in a fully digital world where there are a lot of different sources coming in. Defining and scoping is another whole category of challenges. How do we compile an ASOT? Where do we go to get those sources? How do we make sure that they're continually bringing things in and they're doing it in a way that is compatible with whatever standards we have, or that it is understandable? We want to make it searchable, but if everybody uses different terms and different standards, that's hard. So that's going to get into the data point that was brought up. What should we include? What's a reasonable scope for an ASOT? If we have an ASOT of a space catalog of debris objects, well, that could be millions if you want this to be really include things that are really, really small. Should it be all sizes or just of a certain threshold? Should it be at all orbits? Should it be just stuff? Should it be just satellites, or does it include debris? All these things are important scope questions when you build an ASOT. And this really fundamental, vexing question of how do you handle derivative sources? So you have an ASOT that maybe was pulled from some other things. You have this database that constitutes the ASOT on some concept, but somebody else now references it in order to either build their own database of things, or maybe it goes into a model. Do we consider those things derivative sources of truth, or do they somehow also represent an original source of truth, and there's a new start here and they have to curate and maintain? There's a lot to track when you start thinking about the full pedigree of any given source of information across the enterprise, and this gets really thorny. So those are all challenges, as well as how do you capture the uncertainty or potential subjectivity of certain types of data when you call it authoritative, but there's inherent uncertainty with it. A classic example here would be a threat database. We have intelligence estimates of certain capabilities, but they often come with conflicting information from different sources or some sort of uncertainty bound. How do you capture that in an ASOT effectively? Data protection. Well, we want to be comprehensive in our data set, at least for whatever scope we've agreed on. But as we've talked about, sharing is pretty hard. We're not good at that in general across the community. And that's not even accounting for the fact that when you aggregate multiple sources of data, you potentially create security issues where things separately were unclassified, but taken together, they can expose some vulnerability. Then there's what I would call synchronization across different boundaries from different networks, different classification levels, different organizations. How do you keep those things in sync? So given all of that, maybe the ASOT concept isn't really a binary thing. This is an ASOT, this isn't, this is certified, this isn't. Maybe it's more of a continuum where there's levels of trust that we try to characterize so that we help users get to the data they need at the time they need it, and we can begin to foster this trust, but not truly in a binary sense. All right, let me stop for a second and catch up on chat. Adjudication is a large challenge. Yeah, who decides? Managing an ASOT across classification barriers. Yep, you got that. That's a good one. One problem I've run into with ASOTs is tracking excursions or variations of a given ASOT. How do you track a known deviation? Yeah, I think that gets into the derived ASOT and which one's truly the ASOT and tracking that. It's a known challenge. Yeah, and when do you actually go back to the original ASOT, and potentially update that? I can only help you admire that challenge. The kinds of things we're looking at to address this in one working group that I'm involved in is this idea of really understanding the pedigree of data and thinking of ASOT as a continuum, that these are better ways to maybe think about the problem. How about applying the systems engineering V to constructing these data sources? Scooter, I don't know if you were being snarky or genuine. I'm not sure what you mean there. Chris says the answers to these questions are extremely dependent on the particular context. Yeah, that's a good observation, Chris. Always depend on end goal of use, data use, and goes back to whether one particular community even considers an ASOT or not. Okay, Scooter, you're being genuine. My system measuring V to constructing these data sources. In terms of like, did that come up as part of the life cycle of an ASOT kind of idea? Depends on the level of integration. Maybe. I'm not sure I have a good answer for you there. Yeah, when to apply the V. Any other thoughts here? This is the end of ASOT, this part of the discussion. So if you have any other questions or thoughts, this is the chance to do it. Are we aerospace or the space community addressing these challenges right now? You mentioned a working group, but has it gone further? Do these need to be fully addressed before we implement? Yeah, lots of people are looking at this in different contexts. And a lot of it does come down to data engineering, data science type things, because fundamentally this idea of an ASOT seems to affect that realm most especially. But there is even the fundamental question. We talked about how ASOTs could be models, they could be people. How on earth do you incorporate that sort of construct into this? But most of the work I see is at what I would call the data layer, standards development, the ability to track individual atomic pieces of data through an enterprise and what that would look like. Not an easy problem, obviously. There is an SE forum presentation this year that provides a deep dive into ASOT. It should be up on Aerospace. That sounds interesting. Okay. Thanks, Kyle. Yeah, Scooter, you mentioned governance. Yeah. This kind of hits on a theme that we're going to have across these challenges and just overall transformation. There are a lot of potential benefits of digital engineering. When we talk about the challenges, a lot of them come down to you've got to have the discipline and willingness to accept other governance constraints in order for this to be sustainable. So in some ways, we gain additional freedom and capabilities. In other ways, there's going to have to be some additional rules that we all agree to in order for this to work. And one key area for that is data provenance and standards that support that. If you want to be in the repository that is just it's not so much a data lake as a data swamp, and you just want to have your data available, okay, that's fine. You don't have to follow some of these structuring rules. But if you want to be at more of this higher level of trust in the repository where things are certified or at least characterized as high trust or an ASOT, well, then you are going to have to conform to certain standards in order for that. A chosen ASOT implies a chosen standard, right? I think so, unless the scope is pretty small. Like, for instance, maybe an ASOT could be the list of PowerPoint presentations that your particular office uses when briefing external entities. It's an ASOT of those presentations. I guess they're all in PowerPoint. Maybe they're PDF, or maybe there's some other form. The interoperability didn't really matter. The standards didn't really matter. But if you wanted it to be integrated with others, then those formats and standards do start to become more important. Yeah, PowerPoint's a standard. I agree. Or maybe you're questioning that. I'd say PowerPoint is a standard. All right, let's switch gears to another fun one. We've already talked about to some extent, and I'm interested to hear how much you guys are comfortable with the idea of digital twins. Let's do another poll here. I'm going to put up 5 definitions this time from across the community. What kind of things are we going to see here? What are the words that are going to reappear multiple times? Entity of interest. Representation again. We're just going to go with that every time. I like it. But it's good. It's right. Twins evolve at the same time. Well, that's good. That implies some linkage between some things. And what are those things? What are those twins that you mentioned, Kyle? Computer model, life cycle, high fidelity. Good. Near or real-time simulation supports that. Good. Cal, I don't know if you wanted to add on to your what do you mean by twins evolve at the same time? The real one that we build, and the digital one is test. Okay, yeah, there's 2 different things out there. That was awesome. Clearly, many of you did have a good sense of digital twins. So let's hit these definitions and pull some of the key salient aspects out of these. So we've got DAU. They talk about the ability to simulate, the idea that it can be enabled by a digital thread, which we're going to hit in a few minutes here. Involves best available models, sensor information, and this idea of mirror. This is critical. You guys already hit on this, the idea of a real one, a digital one. This is what makes it a twin. There's this mirroring idea. It happens over the life of a corresponding physical twin. That's good. Over here, AIAA has representation, so that was called out. We have connected. So this idea, again, of mirroring, synchronization between a physical asset and the virtual representation, which is another word for model. We've established that. So there's a connection between the model and the real world version, and it spans the life cycle. So we see that again. AWS actually has a good description of digital twin, a virtual model of a physical object. Okay, that's what any model does in theory, but the idea here is it actually spans the object's life cycle, and that we have this connection again between the physical object and the model, and that real-time data is sent via sensors or some other instrumentation to the model. IBM talks about representation. Okay, again, we're just saying another word for model, life cycle, updated from real-time data. So there's that idea again. And then the last one down here from the Digital Twin Consortium is a good pithy definition I like. Representation of a real-world entity synchronized at some frequency and fidelity. So we actually have a decent consensus here across the community of what this is. And some of the key takeaways you see, the themes are, it is a model. We see representation and the idea of a model again and again. Okay, digital twin is a model, but it's more than your everyday model. It's correlated to a specific physical instance. And like Scooter said, the digital twins tend to be, just by virtue of what we're talking about here, very high fidelity. They tend to be more expansive, encompass greater scope than just, okay, it's this one black box or this one module, one subcomponent. It tends to be an entire system. And if it's not the actual simulation, the digital twin is readily simulatable. And Scooter, I think you mentioned that as well. That's absolutely a key part we see with digital twins. But fundamentally, it's this idea that they are integrated. There's a virtual representation and the real world representation, and there's a synchronization between them so that that model is updated. The digital twin is going to evolve across the life cycle. And like all models, it should be fit for purpose. So this picture down here is a way to try to depict this, that standard models tend to be more narrowly scoped. They tend to be short-lived, like they're for a particular part of the life cycle. You know, maybe we built one specifically for thermal vac, or we built one for test, or whatever purpose. And they tend to be relatively static, and we move on to something else. And then they inform our development and design of that real-world entity. The difference with a digital twin is that it has that broader scope. It tends to endure across the life cycle, and it is continually updated. It's not static at all. And you have that two-way connection. Not only is it informing the real-world entity, but you have these updates back to the digital twin to make sure it's as in sync as it can be with that real-world entity. So that makes sense now that we have something that can extend across the life cycle into operations. Checking the chat. It's physics, all physics. Can we have two models being a digital twin with one another? Keep going, Justin. I'm not sure if I track.
No, that's exactly it. So I build a prototype. Right now, it's digital twin is off a real world entity. But can I build a prototype that's really a model, and then have a digital twin to that prototype in order to kind of take him on two different excursions to try to figure out where I'm going? Or is that a whole separate vernacular that I'm getting into?
I think you're getting into a separate vernacular. I think there's pretty good consensus across the community that until you have a physical object, some entity in the real world, it's not a twin. But that does beg the question if maybe we need additional terminology for these other things that are in between. Like I've heard, digital infant, or there's something else. It's not coming to mind right now of what these other concepts would be as part of a continuum of evolving high fidelity models. What do you call a digital twin before there's any physical instance of it? Let's say we're at PDR, we haven't built anything, and we totally plan to have a digital twin. Is it a digital pre-twin? I don't know. Oops. Functional model. Yeah, I mean, at that point, it is that. But if you have the intent to make it a twin, is there some way that you mark it differently or treat it differently, knowing that you will soon have a physical counterpart for it, and it's tracked separately, it's named differently? I don't know. These are part of what we're trying to figure out. I call it the first part. Yeah, until we have that counterpart. Go ahead.
It's really important to understand that when you have a digital twin, I mean, for you to have a digital twin, you have to have a physical counterpart. And the reason is behind that is that while we try to make a digital twin representative of the physical component as much as possible as identical, even identical twins are not completely identical. It is a twin. It is not a duplication.
Yeah, yeah, absolutely. Really, I think anybody who understands why we model gets the point you're making, right? It never makes sense to have an exact doppelganger, but you have it sufficiently high fidelity to answer your questions, to be fit for purpose for your needs. And so in theory, a digital twin could be a low fidelity version. It's just, it doesn't make sense probably cost effectively to do that because there's a lot of investment to maintain that synchronization. Let's see another chat. Differentiator right now be close to the real model is compared to the operating system or SOS. There's a gray area between a model and simulation. Digital twins are more along the lines of simulations and model. They're certainly simulatable. I'd go with depending on the questions you want to answer, maybe it's more technically model if you want to make that distinction, but simulation is an absolutely key part of understanding the behaviors over time of the physical object. All right, so why are digital twins such a big deal? Like the kind of obvious stuff that I'm guessing you guys get intuitively. So we talked about models, like a lot of folks in the line have experience with models. You're going to get all those benefits of a high fidelity model. You answer questions that cannot reasonably be answered by the real world entity because it's too expensive to do so, or it's destructive in some way, and so that it's too precious to waste this. Maybe it's too contentious. We're trying to model some sensitive engagements in space, and we can't do that in the real world. We want to model it. Okay, so digital twins provide that like any model. But in addition to all of that, we potentially get the ability to answer questions a lot better and a lot earlier in the life cycle because we have that model to play with, that twin of the real version. So maybe we can do more robust testing. We can do more integrated testing with multiple digital twins coming together. We can identify these interface issues, which always seem to get us a lot sooner. We can directly support operations well before the actual article is deployed. Maybe we can assess some novel tactics using the digital twin. We can do better operator training well before it's, we don't have to spend as much time after a deployment in terms of checkout activities because the operators are already ready to go. From their perspective, they've flown the satellite already. And when we have anomalies, there are a lot more things that we can do in terms of anomaly resolution when we have the digital twin available to us. That maybe we're a little more comfortable making changes, to a software update with the digital twin than the real article, for instance. And what this can do is drive fundamental changes to the paradigm of capability development. This realization of development and operations, and this fuzziness we're trying to get to with the boundary between the two. That it isn't just development and then operations. It's more of a continuous improvement process, and there isn't such a bright line between the two. Digital twin is key to achieving that. And digital twin also enables this idea of system collaboration, enterprise integration, because we have that model to share with others, and in theory, they can share back, and we can begin to make these connections a lot better and a lot sooner than when we field them and learn things the hard way. Let's see me catch up on chat. Downsides are potentially massive runtime computing cost. Yes, the more complex the system, the more overlapping analyses are desired, the harder it is to actually get results. Yeah, next slide will actually get to challenges. That's a good one. That's why I put the caveat near, okay. So let's go back to the house example one more time, just to make sure that this concept is resonating with everybody and simplifying a little bit. It's one thing to have a model of the house, say the floor plans, at the developer's office or filed with the county. That could be useful to a contractor who's adding a sunroom to your house, but those plans could easily be out of date. They might not reflect other important factors like how the homeowner's been using the house, maybe changes they've made that aren't reflecting those floor plans, or the electrical load, the behavior kind of stuff that isn't going to be reflected in those plans. So imagine if the model of the house was digital, was synced to the real house such that it was current at all times and it was usable by anyone for good purposes for the contractor, maybe less good purposes for the tax assessor who sees your changes. But the idea being everybody knows what the latest truth is here. This is why digital twin is connected to the idea of ASOT as well. Let's hit those challenges. So there are differing perceptions of what a digital twin is and whether there are real world value added use cases. So the reason I say that is, although the definitions I put up there were largely in accord, you will routinely see people use the term digital twin to just mean a high fidelity model. They're just kind of using it as a buzzword because they hear it all the time, or they want to maybe impress, hey, we're doing a digital twin. And what they really mean is they're just doing a model. Unless you have these other aspects we talked about, it's not a digital twin in the strict sense. Then there's the question of what are the use cases that drive this value and make it worth doing. I talked about some on the previous slide, but we're learning this as we go right now about where it's going to make the most sense to have a digital twin. Obviously, if you're going to have the synchronization, you do need some sort of instrumentation, a source of telemetry on the real world entity that communicates back to the digital model. And then that comes with other processes and mechanisms for managing the telemetry data. All of that creates a burden. It's going to add cost to creating those, putting those on the physical device, adds weight to it, risk, complexity. And those are all potential downsides of keeping the synchronization. So the entire digital twin construct and the maintenance requires some additional resource investment to make that happen. There's also another question. This idea of data protection is coming up again. There's sensitivity of data that comes from the operational asset that is different than the kind of data you were getting during development. And so that has to be potentially more carefully controlled. And then data management, who owns and maintains all of this data coming down over the life cycle, and how do we ensure that all of this data is configuration managed, interoperable from potentially different sets. So again, you see these themes again and again. Catching up on chat. Use case, predictive maintenance. That is a good one. I really should have added that. I like that a lot. For Space Force training or U.S. Air Force and training TTPs, is flight sim equal to digital twin? I don't think it's quite the same thing, though I could see a digital twin contributing to that. That, for instance, they have their flight simulator up and they are pulling in the latest digital twin for that. So I call it another good use case. And Scooter, you put it in the digital twin category. I'm down with that. Boeing claims their T-7A was built in a digital environment. Are they the first to use a digital? I don't know. I'll turn that over to folks on the line who might be able to answer that better.
Digital twin concept for which category of, or which market segment? Because you could claim that GE Turbine had been doing that at least before 2016. And then there's always the race car. There's always the race car example
Formula One.
Other people like to put up.
Yeah, if anybody's interested in this, my fault for not including some more examples here, but Formula One is a really fun one where they've done this at large scale. All right, anything else on digital twin? Because this is the last slide on it before we move on to the idea of data centric. So Space Force, their vision for a digital service, they talk about this a little bit, and the idea of maximizing the extent in which personnel prioritize data, first products, to do their jobs and to increase speed and have these other benefits, effectiveness of information exchange and decision-making that was mentioned. That the DoD data strategy talks about being a data-centric organization, and that is an organization that uses data at speed and operational advantage and increased efficiency. So again, there's more of this discussion of the benefits of data-centric versus really what it is. So we need to start to get into that. And I'll tell you, as I go through these 5 key concepts related to DE, they are going to get a little fuzzier. You know, ASAL was pretty straightforward, digital twin pretty straightforward. We get into data-centric, digital thread, it's going to not be as clear. And so that's part of just understanding the landscape here, is where we do have clarity in these concepts and where there may be some ambiguity. The key takeaways here I would offer you are, yeah, there aren't a lot of official definitions to guide us, whether we just talk about the DoD or we look broader. There isn't an authoritative source to go to. This is what data-centric means. It means a lot of different things to a lot of different communities. The idea, though, as you see in these themes, and I think is reasonable when you hear people talk about why data-centric is important, is this idea we want to improve the effectiveness and efficiency of using data for some greater purpose, that we rely on it as a strategic asset. And there's some implied questions here. How do we effectively federate knowledge and support this effective decision-making? How do we achieve interoperability across an enterprise? And several of you have already hit on this as challenges related to focusing on the data layer. So yeah, there's that little screenshot in the bottom right I have from the agenda, the topics we're going to hit, or actually in this case, it was just from the benefits of MBSC and DE. I highlighted the ability to manage complexity, the ability to integrate across the enterprise and do these data exchanges. These are the pieces that really rely on a data-centric principle in order to get there. And so what does it mean to be data-centric? Well, I mentioned treating it as its own important asset, that data is a strategically valuable thing to your organization. You want to separate out the data as much as possible from the tools or the applications that manipulate that data, that you actually have a boundary between them, and that there's a life cycle for data which is independent of the applications and systems that create and use it. And so the core premise here of data-centric really is this: the data is persistent. It has inherent value. And all these tools over here on the other side that access the data, they're fundamentally transitory. They have their own shorter life cycle. They're secondary to the data. That's what matters. That's what it means to be data-centric at its heart. If you're going to do that, though, there's a lot of open challenges. And the idea here is you can overcome some of these interoperability challenges if you focus on the data layer. That is a more effective, a more flexible way to get at interoperability, and really more sustainable, because you aren't constantly trying to keep up with the latest tools and tool standards and getting interfaces between them. You're focusing at the data layer that does have this enduring presence. And if you can get agreement on the ways in which to represent that data, you can bypass all these transitory tools. In this way, you're agnostic to the hardware, the environment or platform you're on. It really doesn't matter if you're focused on the data, you're agnostic to the software. But it does mean there are some other implications to how you handle the data. And so then these next three bullets about visible and accessible, the idea that it's understandable and it's consistent from a semantic perspective, these get into this idea of what's called VALTIS, the acronym on the right there that represents the DoD strategy goals related to data: visible, accessible, understandable, and so on, all the way down to secure. VALTIS. This is how the DoD is looking to implement, from at least a strategic perspective, this idea of data centrism. So in practice, it probably means that data's got to be expressed in open standards, or potentially has to be self-describing in some way. What that looks like, that's all to be determined for a given community. Also, a critical enabler for AI and machine learning technologies and approaches that they access this information at the data level. Those are very data heavy kind of domains. And ultimately, it's very central to the realization of DE. If we're going to interoperate, the idea is we can do it on an effective basis at the data level. All right, let me head over to chat. Yeah, tool agnosticism, we talked about that. Standards become apparent important. Yep. A question from Brian: how do you define data that is agnostic to all software platform types? Software often updates and requires different inputs. How do you make data work for any possibles? Yeah, in a priori, I don't know that I have an answer for that. But if you have standards for the data, on what the semantic construct is for how it's represented, what the different fields mean, and you expose that in some manner, either through a published standard or a tag that self-describes that so that it can be interpreted, you should be able to have compatibility with the tools. Yeah, and the idea of data centrism is software has to design to that data. So if the data is stable and consistent, the onus does become on the tools to be able to conform that. Okay, let's hit challenges here. Same thing we've done for the other categories. Let's talk a little bit about the challenges. There's going to be some investments in people, policies, processes, because we need new skill sets here. We need people serving as data stewards, custodians of the data, managers, governance kind of functionalities, in order to do this, to establish the standards, enforce them. There are just new roles to do that. Now, some of this potentially could be automated, but there are new skill sets required for that, and new policies. There should be mechanisms, hopefully automated, to track the data across its life cycle, to understand its pedigree. We talked about this in the context of an ASOT, how you really know where data came from, whether you can trust it, and all those elements of VALTIS. Is it truly visible? Is it accessible, understandable, secure, and such? And then again, the governance processes and approaches to ensure it's being managed correctly and that we're conforming to the right security practices. Then there's this culture piece. We've got to have some changes in place that incentivize greater sharing of data for the benefit of everyone. The typical culture here, the default, and here I mean, our world, the space enterprise in general, is, protect your data. It's mine. I'm not going to share it. I'm concerned with what you'll do with this, how I may be held accountable for something. All of that's a big challenge here related to data centricism and DE writ large. And the fact remains that many of the tools, many of the models we develop, they're not, the models themselves are not tool agnostic, and the embedding, the relationship between models and data, which was already discussed a little bit earlier, isn't always clear cut. Sometimes the data is embedded in the tool itself. And so how do you make these separations that are critical to actually being data centric? Things are going to have to be refactored for that to work. Implications to ASOT? Well, like I hinted at earlier, maybe it's more of a continuum based on data lineage strategies. And maybe instead of things are an ASOT or not, based on the underlying data, there's a degree of ASOTness that we try to capture and communicate to users. I head over to chat. How do you share between organizations with vastly different software? Well, the premise there, Brian, is it doesn't matter anyway. The different software doesn't matter. It's the data layer. So we're agnostic to that. As long as we agree on the standards for representing the data, it doesn't matter at all anything about the software, which is the beauty of this. And I don't mean to suggest that that's easy, but that problem is the argument for why this is so potentially powerful. Yeah, and Jeffrey hits that. Okay, good. Thanks, Scooter. Anything else on data centric? All right, let's go to the ecosystem. Another term I'm sure everybody's heard at one point or another. What kinds of things are part of an ecosystem? I've got 3 definitions for you here, all DoD based. What kind of words and terms are going to creep up here repeatedly? Yeah, so here's what the 3 definitions I pulled in there across the community, at least relevant to our community for a digital engineering ecosystem. You've got DAU, Space Force again, in a couple places. So upper left, DAU, it has the idea of infrastructure, environment. Yeah, that it's interconnected and it includes processes, methods, tools, and then the kinds of things it does, capabilities that was mentioned in chat, and it meets the needs of the stakeholders in some way. On the right, you have, again, interconnected infrastructure, environment, very similar sort of definition, just a little bit different focus. And then at the bottom, it's got a little bit broader explanation of the idea of an ecosystem, and that this is an excerpt where it talks about improving and accelerating the capability lifecycle is dependent on this idea of having the right digital infrastructure. That we have state-of-the-art capabilities, they're interoperable, the networks are supportive, they're up and going, and we're not worried about the speed because everything's just where you need it when you need it. And then on top of that are these tools, these applications, interfaces. So you can see already the ecosystem is a pretty broad thing. It's not just the IT infrastructure. It's not just the networks, but it's these other things that fit in there in order to allow users to access it effectively, to get to that data and models analysis and do what they need to across the ecosystem. So key takeaways here. A DE ecosystem, pretty much anybody's conception of this, it's got to have this interoperability to it. It's interconnected. We've talked about the importance of making all these connections to manage the complexity. Well, you need to have the mechanisms to do that, and the ecosystem is the heart of that. It includes infrastructure. We'll talk more specific about what these mean, but basically IT infrastructure, networks type stuff, environments, the platforms where you work, the tools and applications that allow users to interface with it. All of this is part of most conceptions of what a digital engineering ecosystem is. Basically, it's everything needed to enable this vision of digital engineering to actually work.
Hey, Aaron, Justin, again.
Hey, Justin. No, go ahead.
What's the forcing function to ensure that we get the ecosystem? Because I agree with everything that's on this that's on my screen. what I'm concerned about is there's no forcing function to actually develop the ecosystem right now. That everybody is still able to develop the way they want to, and therefore we will never get to the digital engineering ecosystem and never realize what's being stated, because there is no forcing function. There is either no, programs aren't being told to go back and rework their program to get into the ecosystem, or money's not being shut off until they do something like that, or so I see this and I go, it's aspirational right now because there isn't a forcing function. Sorry, I know that's probably beyond this, but I think each of us will run into this in some point in time where we go, okay, what is the need for the greater good, rather than what's the need for my specific program that I'm working on.
Yeah, that theme keeps coming up, doesn't it?
Yeah. So
no, it's not beyond this at all, Justin. In fact, let me defer your question just a couple slides to the challenges, and the points you bring up, I think I hit on as well.
Got it. Thank you.
We'll admire the problem together. So why is a DE ecosystem such a big deal? Let's ask this question again. It's directly linked to two more goals in the DoD digital engineering strategy, but it's this idea that it serves as the foundation for enabling digital engineering. It's doing knowledge management at a much larger scale, so you've got to have the support technical foundation to make that happen. But I think that's clear. Let's move to those challenges that you were starting to hit on, Justin. So first, let me just talk about what almost always happens when you talk about an ecosystem, at least at a large scale in a cost-effective fashion, and that is these cloud technologies. This is what has started to make all of this much more reality. I mentioned earlier, a lot of this was very aspirational for a long time, and it wasn't really realizable until you have an ecosystem to pull it together. And the realization of an ecosystem wasn't very feasible until the last 5+ years as these cloud technologies really matured. So when you hear about an ecosystem, you almost always hear in the next sentence something about cloud services or cloud computing capabilities. And this is the idea that this is what makes the return on investment cost effective. This is what makes it compelling. This idea that you have shared pools of readily configurable hardware and software resources that are really easy to provision for your needs. And it's almost always accessed via the internet in some way, either with that way is to a local network, like an on-prem private cloud solution, or to a public cloud provider like these three shown there at the right. And those are the big three, and it shows their market share as of the last month or two. AWS is the biggest player, but the other two are trying to catch up, obviously. You've got all these kinds of capabilities that we need for really any business, but I'm listing things there that hopefully resonate with our community. Compute and store, everybody does, but we've got a lot of software development activities. We have a lot of databasing, a lot of analysis, and AI machine learning, and the collaboration functions. Again, these are things a lot of companies do, but these are the kinds of things that we can do effectively in a cloud architecture. And so there's this idea, you'll hear this term elasticity, or even just democratization of IT. That's what cloud brings to the table, because you only use what you need when you need it. Okay, challenges. That very first bullet is, I think, a roll-up of some of the things that you started to get to, Justin. That yes, there's a large investment, but when I say outside of typical funding channels, that immediately gets to the problem of, okay, how do we actually make this happen? How do we get started on doing this when this type of capability is inherently cross-cutting? It's not like any individual program is going to go fund all this, and it's in everybody's best interest, but funding typically goes through the acquisition channels. So here's this large investment we need in IT and to build out this ecosystem and make it happen. Where is it going to get allocated? Who's going to control those funds, and yada, yada. So what you brought up, Justin, is a challenge we see with a lot of our customers, knowing they need to invest in ecosystem type stuff at a large scale for this to be effective, but unable to do so because of budgetary, bureaucratic constraints like this. So what we're typically seeing is little enclaves of ecosystems that are being built up. One individual organization or one lab somewhere works with cloud provider and gets their stuff up and going, but it's balkanized essentially, and it's going to be that much harder at a later point to bring it together because of this reality. Aerospace has committed to doing this, and I'll talk about this more in the last section. We recognize the importance of this, and we are going to have our own ecosystem for aerospace, but we desperately want to make this federated with what's happening with our customers as well. So that's a key part of this challenge for us. Justin, I don't know if you wanted to add anything else there, but that's what I had to say about what you brought up, which was a really important point.
Yeah, I see cloud as part of the ecosystem, but I don't see it as the only part of the ecosystem. I see it. I see the data exchange between systems without the cloud, also part of that ecosystem. And the issue that we're running into, and I experienced it yesterday when I was working with a program that's transitioning from AFRL to SSC, where the data standards that AFRL is using are not the same data standards that are being used by the rest of the DoD, and they could get away with it because there's R&D. And so then it was like, okay, now how do we change those data standards to fit with the rest of the ecosystem, not just from an AWS perspective? Because I can put, if my data standards are all alphas, and then but you use all numerics in that, I can still put it in the cloud, because the cloud is just a place to store it. It doesn't necessarily provide a standard by which I need to use.
Exactly.
And so that's where I see that ecosystem is, from the digital engineering perspective. I don't see anyone being forceful in saying these are the standards that we need to be using in order to ensure that this ecosystem works correctly. And because the ecosystem, that it's the data ecosystem that is going to drive the interoperability and the integration between the different pieces. That's my perspective. And like I said, I'm experiencing it here at Vandenberg as we're trying to transition programs onto an ops floor. And what we're finding is that, we've got 20 different standards that we now have to somehow integrate, and it's being left to the guys here at Vandenberg because because nobody did the hard work early on and said this is the standard by which everybody else will work. So that's my complaint, I guess. So thank you for letting me get that off my chest. I feel much better. All the rest of you appreciate that. So thanks.
No, we all feel worse. But in the last section, Justin, I'll be talking about the aerospace specific strategy to building up our ecosystem. And we are grappling with the challenge you described. I think we have a good way forward on how to get at this. We certainly recognize that it is more than just the cloud infrastructure, but it's these other things that I kind of hit here in the challenges that I call ConOps sort of stuff. What are the actual workflows that enable these digital engineering capabilities, and how does that potentially imply certain standards in order to affect these? So, yeah, this is part of what we're dealing with. Also, there I'll briefly hit just the question of cloud versus not. Cloud isn't the complete answer, like Justin was saying. There are architecture questions about where cloud makes sense and where it doesn't. I mean, for instance, high-powered compute is a place where cloud is starting to catch up, but for a lot of applications that are extremely critical on latency timelines, that on-prem sort of solution or something more local is critical. Or really hard questions that we've got to deal with at Aerospace. Do we go with a single cloud provider that's going to simplify a lot of these workflows and have everything go to one place? Or do we want to, from a strategic perspective, actually deal with multiple cloud providers that may help us better inform our customers on where they need to go, because they're certainly not all going to the same source. So those are some of the challenges we've got to think about. All right, let me bring this up and acknowledge what I suggested earlier, or at least hinted at, is these get more fuzzy as you go along. So this thread one is kind of fuzzy. So I want to point out some of the key themes and then try to bring it together into a single concept that hopefully resonates. So you see this idea of enterprise level. That was in the chat. That was good. It's an analytical framework. It has the interplay of all these different things: authoritative technical data. So we see authoritative again, software, information, knowledge, data. It helps decision makers, and it does so across the life cycle. So you see those themes again. Correlating information across multiple dimensions across the life cycle. This is Digital Twin Consortium. Let me also hit this one down here. It's out of an academic paper that was good. A data-driven architecture of, so it implies that you're data-driven for a digital thread. You have these shared resources. It uses authoritative data, and it becomes the communication platform, which I think is also a potentially useful way to think about this. We'll talk about in the next slide. And then there's this excerpt from There Is No Spoon. If you're not familiar with this or haven't read it, at least scan it if you're interested in this at all. It's an interesting read from Will Roper, who since left the DoD, probably just out of sheer frustration. But he has this interesting depiction of digital thread and tries to explain how it connects all these models across the life cycle. And he does it in the context of a lot of matrix-themed explanations. So key takeaways for thread. Here's what I offer you. This is a more emerging concept than the other things we've talked about, but it may just be this idea of an evolving, intertwined model of models and how that all fits together. You know, going back to the last page here, and this graphic out of the academic paper that talks about a total thread, and there's different models that enter at different points in the life cycle to represent that overall thread. But it's probably available to all stakeholders who are interested in it, helps manage the complexity, informed decision making. But this accessibility extends across both space, people, and time. So there can be elements or model components that are available earlier than you might otherwise expect that can help inform other parts of the thread. And so this is going to get to an idea of collapsing the life cycle that the digital threads hope to do. So maybe a digital thread is really just a virtual record of a system, very comprehensive, or maybe multiple systems. It exists across the life cycle, and it tries to integrate all this knowledge together so that you're fundamentally not throwing things over the wall, that you do one particular analysis, you have a set of models, and you send it over to somebody else, the results of that. Instead of that, you're working from a common modeling environment, a thread of different models. And instead of sending the model over, maybe as part of a workflow, they're informed that this piece is now ready and you can take their analysis and incorporate it into your own. It's anchored to data-centric. That was definitely a theme out of the definitions. Uses digital twins, relies on an ASOT. But maybe it's an ASOT on steroids, you know. Whereas before ASOT, or at least the definition and scope we described of an ASOT is probably relatively small. It's a given community of interest. The idea of the digital thread is this is the collection of ASOTs and models that everybody agrees to work from. And so I mentioned the idea of lifecycle being collapsed. Maybe we're less dependent on a sequential milestone-based strategy if we have digital threads, that you could do that analysis of alternatives early on and do it with greater fidelity than possible because you have this thread already built up, and maybe you're pulling from a thread of another like system to even populate your initial stages. Maybe test can occur in a very meaningful fashion before design is complete, and so on. So these are the kind of things that might change. Maybe requirements are embedded into models from early design all the way through manufacturing, and we can understand whether requirements are being satisfied and closed with a lot more confidence. In terms of challenges here, well, it sounds pretty aspirational, so maybe some of the challenges are pretty obvious, but certainly, again, we see these themes of culture, security with the data aggregation and management, and interoperability of the data to make this happen, because this is really the synthesis of a lot of the other concepts we just talked about. So it incorporates the same challenges, but at larger scale. Scooter, how different parts of the organization come together to participate in the overall DE effort? I'm not tracking, Scooter. Is that a question? Or were you answering someone else's? How different parts of the organization come together to participate in the overall DE effort?
It was more along the lines of answering the question, what is a digital thread?
Oh, yeah, I don't disagree with that one. Yeah, it's this idea that accessible to all stakeholders, managing that complexity. Good. Anything else on digital thread?
But Aaron, the intent of the digital thread is to combine a bunch of things together so you get a singular outcome, and as opposed to multiple different outcomes, correct?
Yeah.
So I'm bringing all these different things together in order to improve my workflow, or in order to make sure, something else happens, not to then, go out and bulk, your word, balkanize again, where everything just splits apart. Okay. I just wanted to make sure.
I think so.
I just wanted to make sure that's what I heard, that's what I heard, and what you said were the same thing. So.
Yeah. Acknowledging that digital thread is much more of a squishy concept, such that I think you'll hear a lot of different impressions, but what you just said back to me is how I think of it. Yeah. And a set of digital streams connecting synchronized simulations. Would that be a practical? That's interesting. I like the streams and the synchronization. I get a little hung up on the simulations because I think it's a lot more than that, but I guess a key part of it. Because it's really that overall knowledge management, not just the simulation. All right, let's review what we talked about in this section with the, more advanced key terms in DE. In ASOT, let's do the same thing we did before. How would you explain this in really clear, simple language with a few, short sentence to somebody who maybe wasn't even at this course? What is an ASOT? Yeah, Anthony, toughest concept so far. I agree. Central reference for models and data. Good. The trusted source of data. Source data agreed upon by enough people. Again, yeah, enough idea. Good. Yeah, so authoritative source of truth is accepted by a particular community for their purposes. It's a trusted source for them. And, we dig in that a little deeper, and maybe ASOT is a little bit less binary than that, but that's the basic idea that we're talking about. What about digital twin? What were the key aspects of a digital twin? Like, why is it different than a model? Something that mirrors its real life twin. Good, mirror. Again, that synchronization, updated from real-time data. Good. You guys got it. Special type of model, probably evolving, probably almost certainly supports simulation. We have that behavior aspect, but it is linked and synced to that real world counterpart. Good. Not data-centric. What does that mean? If we're going to be data-centric organization, or somebody wants to be data-centric, how do they treat data? Prioritizing data over apps, exactly right. Thinking in terms of data, strategic asset. Yeah, data is key, tools not so much. Now, a lot of people may not agree with that approach, but that is definitely the premise. So regarding data is central. It's the permanent asset. It's what matters to an enterprise, and that's where you do your knowledge exchange wherever possible. And informs decision making. Yeah, that's good, Rob. The ecosystem, I was going to hit that one already. Everything needed to enable DE to work includes the infrastructure, environments, and applications, and the users. That's probably part of it as well, though not all definitions include that. And then let me reveal digital thread too, since that one's fuzzy anyway. One way to describe this could be, in just simple terms, it's a virtual record. It's available to everybody who needs it, and it's going to exist across the life cycle and encompass all these different pieces in digital space, such that we hopefully aren't as constrained by typical life cycle sequencing. We can do things out of order and better and different than before. All right, that concludes section 3. Let me stop here for any other questions, comments, or discussion related to key DE concepts. Okay, let's go to the next section, be what I'm calling beyond the basics of digital engineering. And we'll talk about the relationship between DE and M&S. We've already hit on that a bit. Talk about it some more. What's actually happening in digital engineering today? I'll give you some series of brief examples just to help bring this home, hopefully. And then what are the biggest challenges with DE overall? This will incorporate some of the things we've already talked about as well as some other things. So when we consider modeling and simulation, here again, we see it's called out in the DoD strategy to directly inform decision-making. So it's objective number one. So all these themes are showing up in the DoD digital engineering strategy. If you haven't read it, if you aren't familiar with it, you want to learn more, absolutely start there. It's a good overview of a lot of these things. And even though it's 5 years old, it got a lot of things right. And even though we've evolved beyond it, it's a good starting point. So digital engineering, we're applying these modern technologies. We're doing it at an enterprise scale rather than just a system. We want to do all these engineering functions and maybe more, do them in new ways, improve efficiency, improve effectiveness, manage complexity, better decision making, all that kind of stuff we talked about. The idea is we're continually evolving these authoritative sources of truth and that they're highly accessible to all the community. We have good interfaces to get to them. They're modular, scalable, readily implementable, and we have these solutions across an entire ecosystem. Can you see this? You see this diagram of you've got data and models, we've got the tools and applications to access them, and we've got the infrastructure to support all this. So that's kind of the digital engineering side of things, a little bit of a summary of what we talked about. Let's switch to M&S. Well, you think of modeling and simulation is the use of these models in some sort of workflow, again, using modern infrastructure to produce data or some other way to inform decision making for ourselves or our customers. We're trying to break down these stovepipes as part of all these M&S efforts and the modernization of M&S. We want to do this across the enterprise. We want to do it effectively, efficiently. All these same themes. So the way we're thinking about this, especially at Aerospace, and I think is accepted across the kind of communities that do M&S a lot, is these are really two sides of the same coin. And that we have these data and models that inform analysis products, and we have these tools and applications that enable effective M&S workflows, and that they all rely on this common IT infrastructure to make these workflows effective. So you'll see this again when I talk about how Aerospace is tackling the overall transformation problem, how we've organized into particular lines of effort to get after this. At the heart of this is recognizing this joint relationship and symbiosis between digital engineering overall and modeling and simulation capabilities. Are there any questions, comments, or discussion here?
Hey, Aaron, all right, just because I just stop talking. So as I'm going through this and I'm looking through this and I'm starting to think about my time working with OVs and SVs. So the DODAF framework fits nicely into kind of the DE and model building that, is required for JSIDs, is required for building systems. And I know everybody wants to get away from that, but there's a forcing function by using those DODAF models to, and it gets you to a very low level or a high fidelity level.
It can, yeah.
In all the rest if used correctly. So is it one of those where, from an aerospace perspective, do we need to maybe start teaching a little bit more of the DODAF side of the house to at least give people an introduction as part of the DE and as part of MBSE?
Well, that's a tougher question. I guess I would offer that anything that's specific framework related or tool related or language driven, those are probably things that we want to allow customers to use and users to use on an as needed basis for their purposes. So we don't want, I think we, and the we here, and when I use it in this context, is like the digital engineering integration office and trying to transform aerospace. I think we want to come up with solutions that are in no way, that are agnostic to the tools, that is data centric, such that specific modeling frameworks, languages, and tools are not part of the solution and can be used and changed as needed for specific users.
Okay, that's a fair response. I would just go back and say that
Somebody may still need to enforce, you shall.
well, it
do
becomes
such and such.
easier to get things through the Pentagon. It gets easier to interface with in a multi-domain environment when you go to the DoD architecture framework, and because they're doing MBSE, but they're doing it from an architecture framework perspective in most cases. And like I said, I know there's a lot of people pushing hard to say we don't want the DODAF model, but when you start,
plus we have a lot of non-DoD customers, right?
Right. So okay, fair. I'll shut up for at least 15 minutes.
All right, well, that's good. Thanks. Chat. Key aspect of working with sensor class data is need to know: is DE anathema to data segregation needed to meet security requirements? Looking at that's a good question, James. I'll hit on that a little bit here in the challenges. You've really teed it up well. Before that, though, let me hit a couple more slides just on some examples, things that are happening that are at least down the road of digital engineering. So if you go back to that idea of a continuum, and you've got MBSE on the left and DE on the right, and we're trying to move toward the right. None of these are fully on the right, but they at least have some flavor of that. So let me talk about these a little bit and what they're trying to do. There's the NSTTC, National Space Test and Training Complex. This is a STARCOM initiative to try to build out this fully accredited, fully digital representation of the national security space enterprise and what that joint warfighting environment would look like to inform testing. And the idea is this would be a full-up digital test range. And the manner in which we have to conduct testing in space is very different from the other DoD components, and this is a way to try to get at that. So they're exploring a lot of new ways to use M&S tools to help them with training, test, and exercise kind of functions. Another thing going on right now is the U.S. Air Force, the Create Air Vehicle AV. There's a bunch of physics-based, high-performance computing tools that they're using for design analysis of various platforms. Air Vehicle is just the one exemplified here, trying to address the system integration issues, quality, scalability, and so you can see this idea of digital thread. There's digital twin here. There's the idea of connecting these different pieces of the life cycle to form the beginnings of what could consider to be a digital thread framework. More examples. We've hit design reviews a few times today. Well, various organizations have been trying this out, have been doing it to some extent. Sparco, a space Rapid Capabilities Office, they've conducted a couple of incremental styles, so not like really big milestone, but kind of a more of a rolling SRR and SFR for their program. NRO has done multiple classified SRRs in sort of a digital space, or at least model-based, using SysML for a lot of the artifacts, so that they have these model representations of traditional systems engineering artifacts. SSC has connected to the PTS program using materials out of MBSE models, because architecture requirements, which is kind of the low-hanging fruit to do this for. Ecosystems are being developed in a number of places. Justin, you talked about some of the challenges of getting started here. Well, NRO had talked about balkanization happening, but here's an example where it's gone the other way, where the NRO and most of the IC for that matter have been using C2E, the commercial cloud enterprise, C2S, these commercial cloud capabilities to store, access, and other cloud services for a lot of the community. And so this has been happening for several years now. Space Force is trying to implement what they call the Spaceverse. Originally it was called Metaverse, but that was taken by a certain other company. So they switched to Spaceverse, but this idea of having a common environment everybody works in, much more immersive. They're talking about using gaming technologies to try to build this out. SSC is actually charged with a big chunk of this that's focused on the acquisition side to build out their ecosystem. They're starting to get funding to go do that. MDA, the Missile Defense Agency, has developed a federated ecosystem across DE that's really focused on M&S. It's probably the gold standard in terms of sharing common M&S repositories and analysis capabilities across a given organization. So that's happening. More examples, STARS here at Aerospace. This is the telemetry that is coming off various sources that are being brought together to help with launch vehicle and ground system analysis. It's all being done in real time as part of launch operations. It's built on an on-prem version of Aerospace Cloud using what's called E3. I'll talk about that a little bit more later, what we're doing with the enterprise engineering ecosystem here at Aerospace. But this is the idea of an ASOT here. We have a discoverable and accessible data analytics. It's accessible with standard APIs that people can build to so that we have this interoperability. So here's another real ASOT that's happening right now. Enterprise level models across an organization here, it's SSC. They have what's called the BMAP, Blue Model and Assessment Program, that captures a whole lot of essentially the government reference architecture at large scale across all of these systems. There's something similar, analogous to that happening on the threat side, where there's a threat model library that serves as the ASOT for those things, at least for certain communities. Let me also hit, I've got one more page of examples here. Digital Twin Ventures project, also happening here at Aerospace, where we're trying to build out a digital twin by essentially reverse engineering one from the rogue CubeSats, these small guys that were Alpha, Beta, Cube satellite program here at Aerospace. Developing aspects of the digital twin, at least what those would look like at key phases within the life cycle. We talked about how does a digital twin really make sense at concept development before there is such a thing? Well, maybe if there was a physical model built at some point somewhere, we can have one. But what do these things look like? What does the life cycle of a digital twin look like? Trying to even create a manual and specification for how we build this out and get the nomenclature terminology right and what phases of maturity are necessary across this process. So that's the Digital Twin Ventures project. The last one I'll hit here is kind of the granddaddy of digital engineering. I don't mean to suggest that they've got this all figured out, because they don't by any means, but the program Sentinel, which was formerly GBSD, the Global Base Strategic Deterrent, they describe themselves, at least, born digital. They were fully committed to digital engineering right at the beginning. It maybe helps when you have many hundreds of billions of dollars to get after this sort of problem, but they were absolutely committed to doing this. They've done a lot in this space to pave the way to show what's possible. They're routinely delivering models to their contractors as actual specifications, instead of a Word document type thing. The contractors in return are expected to deliver models back to the government, and the government is integrating those models in their common digital environment. So they have essentially a digital engineering ecosystem stood up, and they've done also multiple reviews in at least somewhat model-based digital space. Let me take a break there, see if we got anything new in chat. Is this the same thing as the CDC Digital Twin F, the Ventures Pro? I think it is. Can anybody confirm that? I believe it's the Concept Development Center leading this. If somebody knows, go ahead and add it to the chat to answer your question, Kyle. And Scooter, you make a great point. I probably should have hit is, Sentinel, although an extraordinarily large program in the sense of money invested, has a pretty narrow mission set. And so they have the advantage of not having to connect a lot of external pieces. Now, granted that they've got to connect to the actual weapon, but they have a pretty straightforward problem. It's not as complex as a lot of the space pieces that we deal with. All right, let's hit the challenges. I've got a few pages here, just hitting these 5 major kind of challenges topics. One is getting starting the transformation journey we find as a challenge. One is data management protection. We've talked about that to some extent. Let me hit a few points there. Tools and applications, skill sets and expertise, and then what I call mindsets and culture. It's a big challenge. So for private sector companies, where in general digital engineering is more mature than we're seeing in the DoD, this is not an allowable direct charge to the contract, right? It's an indirect investment. So that makes it challenging, but it's overcomable, it's surmountable. For government agencies, this is just not something that we have ever figured out a way to pay for by program to do digital engineering. So MBSE, we talked about right at the outset, it tends to be more system centric. So you can do MBSE things, start adopting MBSE practices at the system level, and it works. You talk about digital engineering and the scope of integration that's involved. It doesn't really work for each program to go off and do its own thing. We've got to figure out an integrated way to do this. So getting started, part of that is the funding of this, how we do it, but part of it is just not understanding what we're in for here. So we see with a lot of our customers already that they want to do digital engineering, but they're not quite sure what that means or what the use cases are and mission threads that it's going to support. And so it becomes more of a, hey, this sounds cool, let's go do it, versus here's actually what we want to get out of it. And so you kind of get some uncertainty right at the beginning about vision and strategies. And so that needs to be established. There's the organizational commitment pieces, the fact that a lot of resources are required to make this happen across all these pieces we've talked about. The ecosystem, tools are very expensive, governance, data rights, workforce. Again, these are outside of standard funding channels to make these kind of things happen, but they need to happen. Then there's this question we see all the time. I talked about it a little bit earlier with the cost question, the return on investment, what I call the return on investment rabbit hole, where organizations are not willing to commit these resources until they have assurance that they will pay off in the long term. So what I put here up on the screen are a couple excerpts from a RAND report that came out earlier this year that I think is probably the most compelling response to this concern. And it's a perfectly valid question to ask, right? Why should we invest if we don't know what return we're going to get? But as this report makes clear, even though you have these significant investments that are needed, and they're going to take a variety of forms, we talked about that. Look at this bottom portion that says, although there's plenty of anecdotal evidence, people are saying this will work, there's almost no verifiable data to inform cost analysis on the magnitude or likelihood of cost savings generated from DE efforts. So that's a tough reality that we have to embrace. The answers aren't there. So there's kind of a question of faith about whether organizations should head down digital engineering path. And one of the most compelling arguments may be, look what's happening across private sector. They are routinely making these commitments at very large scale. Now, they're not going to share their cost numbers with us for competitive reasons, but seeing that happening is a pretty compelling argument. And then there's this issue, and I just saw this come up in chat. You're exactly right, Helen. This is the same story of systems engineering. Again and again, they're like, I don't want to do systems engineering. Prove to me at work, show me the numbers. And they really weren't there for a long time. But systems engineering has proven to be obviously critical throughout the capability development of DoD. Question here, aren't examples of the cost of systems engineering failures enough? Maybe. You kind of have to have the full picture to know whether the investment costs offset those failures, though, right? Because we are talking about some potential big numbers for the investment. I still go back to, I think the most compelling argument here is, if you want to integrate an enterprise, this is the only feasible way to do it. And it's going to cost what it's going to cost. All right, let's talk about some more challenges related to data management and protection. Anything you guys just want to throw out in the chat here that would fit into this category of a potential challenge? Cameo costs money. Yeah, under tools and applications. Yeah, IA certification. Yeah, I didn't have that one. That's a good one, Justin. PowerPoint is free. Yeah, so why not just use PowerPoint? No cost to me. So this idea of data centricity has all these challenges related to the interoperability and the enforcement and standards, and can we actually communicate at that level? It's a pretty difficult problem in itself. This idea of data lineage, ASOTs, how we manage the configurations and all these standards. Okay, big challenge. But then this other piece of it, the starts to get into culture, the need to share if this is going to work versus the need to protect. There's valid need to protect, and then there's the less valid need to protect. I own this data. I'm not going to share it. It may require new incentives for people to make this happen, and it may require entirely new security constructs that enable this. Things like zero trust, continuous authority to operate. I mean, that's a wonderfully powerful concept in DevSecOps that scares a lot of security folks. And just all of this data, everything we're talking about, the scale, there's risk of information overload. SMEs are going to have access to unprecedented levels and types of data. And maybe we make their lives easier in some respects in terms of offloading some of the unpleasant aspects of doing their job, but there also could be, they have the potential to be overwhelmed by all these other pieces. Yeah, tools not available in SAP environments. Yeah, let me go down to tools and applications. So licensing and deployment strategies. A lot of different options are available with a lot of different ConOps in terms of whether these licenses are shared on a central server or farmed out. How we treat our COTS kind of products versus organically developed things. The overall interoperability of tools. To the extent that we'd like to be data centric, we're not going to be there anytime soon, and there's probably always going to be a need to have some tool communication. What do those workflows look like? How do we manage those? There's not a lot of tools out there that do that, and the ones that are, and this gets to the third bullet, are really expensive. So yeah, Cameo is expensive, but some of these orchestration tools are easily $100K plus a year, and these are order of magnitude kind of bigger than what we're accustomed to. And so there's a lot of new capabilities coming out there for digital engineering workflows and cloud-enabled kind of tools, but those things tend to come at higher cost, at least here in the early stages as they're being fielded. And then like Rob said, yeah, the availability of tools in general across different classification levels is maybe worth hitting on at least briefly. I mentioned heavy use of cloud and ecosystem. The baseline and capabilities across the different classification levels are never going to be the same. There's always delays. You move up the classification levels such that at TS or even all the way up to special access program, the suite of tools that are available and the capabilities will be a much smaller set than what's available commercially and on class. That's just the nature of how this is going to have to work. Is there expectation for price to drop as more people use these tools? Absolutely. I mean, that's just the cycle, right? But we're at the front end of some of these things. So all right, a couple more challenges here. Skill sets and expertise. What do you think some of the big ones are here related to that? Or you jump into mindsets and culture. What new skill sets do you think we're going to have? Conversant with modeling tools. Yep. Government employees way behind defense contractors in DE knowledge. Yeah. And let's hope aerospace isn't as well, but we have work to do. Technical literacy. Getting out of the current way of doing things just works fine. JSIDs, huge obstacle. Yeah. There may be implications beyond digital engineering per se and into processes and governance of acquisition and cost accounting and budgeting. Yeah. So skill sets and expertise, what I've done here for you to think about is, yeah, these practitioners are going to have to do this. And that includes aerospace, that includes CETA, and that includes government to at least understand what they're seeing. They have to become fluent in these modeling languages, these approaches. And effective model-based system engineering requires you not just be good at SC, but you understand modeling as well. So those are skill sets that don't have a lot of overlap in the Venn diagram in today's world. It's going to require a lot of familiarity with cloud technologies and applications, almost certainly. This idea of virtualization, containerization, how we deploy things into cloud, how we actually do software development in a cloud environment. These are very different approaches to how we've traditionally done things. And so it's going to require new skills. A lot of new skills in terms of using tools, and we're probably gonna have to do the idea of upskilling with our employees who are doing this and our managers to understand and interpret these things. And this leads right into mindsets and culture kind of stuff. The technical challenges that I have talked throughout this entire class, they're pretty daunting, right? There's a lot of challenges here we have to think about. It's doable, but and the vision is really enticing, but we've got to overcome these challenges. Even given all of that, the people piece of this is almost certainly much harder. This is what we see from every lesson learned from entities that have completed, and I'll put completed in quotes, that are at least far along in their transformations. The ones that have failed have said this, the ones who have succeeded say the same thing. You have got to address the culture piece head on to have any chance of making this work. In the chat, there were discussion about implications to other things and JSIDs. Yeah, new process and paradigms. I mean, here at Aerospace, what do tours look like? Do they even exist going forward in this kind of world? How do we communicate our products? What are our products? What does a design review look like? How do we do requirements management? All these things could change, and we need to start thinking about what those changes look like in this digital world. The other challenge here is to sustain our traditional missions. Don't lose focus on what we need to do on an ongoing basis while we look for opportunities to do things in a new way and even new missions. And ultimately, how do we incentivize adoption of this? It's one thing if folks agree that this is a great vision and they'd like to do it, but how do we actually help them make it happen in reality? Change is hard. Look at the chat. Mindset culture, biggest barrier, limited availability of expertise as well as tools required clearance. Yeah, the clearance is another aspect of it. I heard about folks working on the DBOK, the digital engineering body of knowledge. Is there a date for public release of it? Would be useful. I'll have to get back to you on that, Kyle. I don't know that the DBOK is going to be the mechanism for trying to get that information out. I'll talk about this a little bit more in the last section about what's going on with our outreach right now and what sources are available, but I'm not sure the DBOK is going to be one of them. I think there's something called the Digital Engineering Guidebook that we're going to go in. Okay, so challenges. Kind of summarizing the challenges overall we talked about in this section and earlier. There's no magic formula for doing a digital transformation, for adopting DE or even adopting MBSE. MBSE can make good systems engineering better, but it's not going to fix bad systems engineering. We can't lose that core skill set. And fundamentally, there's no single blueprint for success in the defense industry. Everyone that we see, that we're interacting with, we're talking to, they're at different points in their journey. Some are very early on and kind of stuck at that, how do I get started? Should I even do this phase? Most of them have started to move out and some things are going well and some things less well. And we have insight into this. And we're trying to learn and apply these things internally. But everybody's journey is going to be a little bit different. And it's not like there is a clear roadmap for this. And then kind of close with this on the challenges. It is not a panacea to be applied universally. DE is something that you've got to figure out and answer right at the beginning. What do I want to get out of this? Why am I doing it? Am I willing to make the investments? So I wanted to close this section with what I'm calling an OV1. Justin, you mentioned DODAF, so this idea of an operational view of what kind of all of these pieces we've talked about up to this point, how they fit together in a picture form. I've never seen anything like this. I've always wanted to see a digital engineering OV1, so I put this together. You guys tell me whether it helps bring all these concepts together, because there's a lot of stuff we talked about. But if you start with this kind of palette of a system in the background, and the first thing you want to put over this is an ecosystem. You want to connect everything and make sure people have access to this. And this ecosystem has all these pieces that we talked about. There's these functions of computing, storing, collaboration, software development, tool availability, collaboration, security, infrastructure. All these things should be provided by your ecosystem. And how we do it, maybe there's on-premises components, maybe there's off-prem, doesn't really matter, but there's an ecosystem where all of this is happening. With that as a backdrop, you then have one of your major pieces of engineering. You're doing model-based engineering, whether that's EE, ME, Aero, or MBSE. And by the way, that's another indicator that we're very late to the game. It's not like EE says, hey, we're doing model-based EE. They just say they're doing EE because that's what they're doing. So maybe someday model-based systems engineering will just be systems engineering, or maybe someday all of this, instead of saying digital engineering, we'll just say we're doing engineering. And maybe there's a piece of non-engineering activities here that goes back to that little bit of fuzziness in the scope of digital engineering, whether it includes things like business processes, maybe, and maybe eventually it ought to. There's one big chunk of work being done, but that's got to be related to the modeling and simulation. I talked about this close relationship between the two. They need to be done harmoniously. So modeling and simulation is supporting those engineering activities, and vice versa. Engineering is supporting modeling and simulation. So fundamentally, how do we anchor and then the data, make sure it's analytically driven to inform decision-making for our customers? Well, this modeling simulation and the engineering need to be working from the same sets of truth, these ASOTs. Underneath that, we've got a digital thread that connects all this across the life cycle, all the phases of design into operations. And throughout this entire thread, if we're data-centric, we've got these data repositories that we're working from. When there's an engineering activity, it pulls from some part of the digital thread that is database driven. The ASOTs are pulling from that actual data or connecting with and updating these various sources of data. Maybe from all of that, we build out a digital twin. We have, from the ASOTs or from some authoritative source, we have a digital twin of a given satellite. But importantly, it's not just one satellite. It's not just one system. It's many systems across an enterprise. And that's where this really builds the depth and complexity. I see any comments here. Let's see, that was to Justin. Okay. Any questions or comments on this big build slide? Okay. Helen, I would like this chart. We'll make all the charts available, Helen. All right, so summary of digital engineering. The only thing left in the course is we're going to talk about how it's happening in aerospace. So this is really a summary of everything we've talked to at this point. In general terms, what is digital engineering? There's this idea of modeling plus systems engineering equals MBSE. There's a heavy reliance of digital engineering on all of model-based engineering, not just MBSE, but it also wants to incorporate things beyond engineering and certainly gets into the operation and mission operations space. There's a huge overlap with modeling and simulation, and the two need to be working together in tandem to bring together the real mission value. Digital engineering is fully applicable to systems and programs, but it really is all about broader than that, multiple systems, and enterprise kind of implementations. It includes not just the models like MBE and MBSE do, but the underlying data, this idea of data-centric, the idea of having ASOTs. That leads to these bigger ideas and really aspirational concepts of a digital thread, digital twin, and what those could do to change the game. It's very reliant, the whole thing, to bring this together and all of these pieces connecting. We have to have an ecosystem that does that. Digital engineering is, again, probably the only feasible, it's certainly the only idea I've heard that has any chance of being able to manage this level of complexity we're talking about, to do enterprise integration, to be more agile across all of these different pieces of the space enterprise. And it does have the potential to be more than just the next thing. It may be an entirely new thing, such that it's a discontinuity from model-based approaches in the past. In general, the transformation in a lot of places is underway, but there are still a lot of challenges, and the manner in which we're going to overcome those challenges, not entirely clear yet. So we're figuring this out as we go in some respects. So that brings us to section 5, which is what's happening at Aerospace in terms of digital engineering. We'll talk about first, what is the Aerospace digital engineering strategy, and what is it that Aerospace is doing to implement DE across the company? In terms of the strategy, we can talk about the vision and the overall strategic goals and objectives Aerospace has established. Got the vision statement here that Aerospace is going to transform into a digital enterprise, and we're going to assist our customers in the same transformation that they're going through, all to advance solutions to our customers' most challenging problems. So that's the overall vision statement that we've established. And the idea is we're going to develop this. We actually developed this through a lot of collaboration across the corporation. It was led by the Enterprise Systems Engineering and DE Corporate Strategic Initiative, coordinated across all the customer-facing groups and various corporate organizations to get their inputs on what we needed to do in terms of the digital transformation. And as you can see from the DoD digital engineering strategy, the data strategy that we've talked about, there's a lot of common themes here. So that's not by accident. We leveraged a lot of that as applicable to aerospace. And you see the strategic goals on the right side, 5 of those. Again, a lot of the same themes we've talked about to this point, leveraging models and data to inform decisions. It's goal number 1. Number 2 is this overall digital information network and the processes and cultures related to that, getting to the idea of an ASOT. Goal 3 relates to standards and DE innovations. Goal 4 is overall infrastructure environment. So that gets back to the ecosystem idea. And then goal number 5 is really about the culture, the people piece of this, and the overall workforce changes that are needed. So in terms of like a mission statement, the idea is we have both an internal piece to account for and the external piece. So to the extent to which we can effectively advise and credibly advise our customers, we have to make sure that we're doing a good job with our own transformation, but make sure that what we're learning informs what we advise our customers. So you see on the left, this piece of ensuring the corporation remains relevant. These are internal objectives and thoughts, ensure that aerospace keeps pace with, fosters digital fluency in all that we do as part of our transformation, modernize our infrastructure, modernize how we do M&S, and that's one part of this balancing act. And on the right side, at the same time, we've got to continue to deliver all the capabilities to our customer like we've done before, but try to figure out new and better ways to do that within this new environment. So provide guidance to them, support the establishment of their ecosystems, and really critically, and one of the biggest challenges is making sure that our ecosystems interoperate. We have a pretty broad customer set. All of them are at different phases of transformation. They all have different ideas for what their ecosystem needs to look like and different levels of maturity for where they're at along that path. We've got to figure out a way for all of this to interoperate if we're going to be the enterprise integrator. So fundamentally, that bang box down at the bottom, aerospace has got to not just fully commit to the digital transformation of our own enterprise, make our own company more competitive, but do it in such a way that we enable ourselves to be the premier integrator across the space enterprise. Aerospace is really uniquely situated to do this. So the idea is if we can figure out how to do this right, we poise both the company as well as our customers in a situation where we can actually be an integrated space enterprise. So that's the idea in terms of vision, objectives, strategy. What does this mean with respect to implementation? What are we actually doing? Well, there's a couple pieces to this. The foremost piece is really organizing to make this change and establishing the necessary governance and authorities to enact it. So the big piece here is the establishment of the Digital Engineering Integration Office. This is stood up over a year ago now, and the overall lead for this effort is essentially the Chief of Digital Engineering. We're responsible, I'm part of this office, so I'm going to say we a few times probably. DEIO is responsible for leading the transformation of all digital engineering across aerospace. So this office is going to provide the overall strategic direction, make sure that we're following the established direction, prioritize tasks, coordinate all the investments, ensure the resources are available, looking across all the different constituencies to balance all of these pieces together to come up with implementations for digital engineering. This office also establishes the overall governance and guidance for DE and the organization responsible for actually recruiting, both from an internal and external perspective, all the skill sets needed in developing digital practitioners that are needed across our company. And the DEIO is responsible for integrating all of these activities in what we call the DE integration framework, and all these different components of transformation across aerospace and all the different people who are affected. So this involves establishing the integrated execution across the fiscal years, coordinating plans for all the projects, whether they're directly funded or indirectly funded. So there's customer funded aspects to this, as well as internal investments. And the EIO also needs to track the progress of all these activities that are happening, make sure that we are on path to achieve our objectives, and identifying any gaps, working all the execution aspects to this. A little more specifically in terms of how the DEIO is structured, the core thought process here is the idea of lines of effort. And you see these relate pretty well back to the objectives established a couple of slides ago as part of the larger strategy. You see first LOE number 1, this line of effort related to governance and integration. This is what ties it all together and seeks to connect these things. LOE number 2 is what we call the infrastructure and environments. This talks about the underlying ecosystem and how we're going to achieve that. Line of effort 3 gets at the core piece of data and models and the idea of ASOTs and how we establish and maintain those and expose those to all the customers who want those. LOE number 4 is capability development and modernization. So now we're talking about specific mission threads and workflows that bring this together, more rapidly delivering capabilities in whatever context, whether internal to the company or supporting that delivery to customers. And then LOE number 5 is that workforce education and culture piece, getting our workforce up to speed, digitally fluent on these capabilities, and ensuring that the culture is tackled as part of this, which is obviously a huge challenge, as we've talked about. So the next few set of slides here, I'm just going to dive into each of these line of efforts just a little bit more, like one slide for each of these. So let's start with LOE number 1, the DE integration network, and this giant connecting chart of all these pieces that need to come together is what's being depicted here. So in the center of this chart, you got the DE integration coordinating with a lot of internal entities, and that's what's happening on the right side. All this kind of light blue and gray, all the different divisions across aerospace and subordinate offices supporting those people. We've established not just the offices, but who these actual technical POCs are and who we routinely interact with, to both status what's happening from their perspective, customers, their needs, as well as what's happening in the world of DE integration, and having that exchange both directions. On the left, you see more of that outward look toward the program offices and NSG, SSG, DSG, CSG, all those entities are represented here. We've got also true external to aerospace connections there in terms of other FFRDCs and UARC entities out to industry with the big primes and what they're doing with digital engineering, and various vendors, largely tool software vendors, and assessing what kinds of support capabilities they provide with licensing strategies and so on. So that's the extent of this very large integration network that's being worked across LOE number 1. LOE number 2, this is the infrastructure environments, really gets at the ecosystem. And this cake chart is meant to depict all the scope that we're talking about relative to the ecosystem. So like we mentioned earlier, any ecosystem has to have this idea of an environment, some sort of core piece of data, models, something that supports the analysis. So the M&S functions here, and then an underlying infrastructure to support all this. So at the top, you've got people. And if you think of this as a cake, those are maybe the candles on top. They're the This is the piece of the overall ecosystem where the people are interacting with the environment in some way to deliver mission value. That green layer, the environment piece, is where they interact. That's where people actually manipulate the data layer in some way through whatever tools and interfaces that we provide. There's that orange layer that we call the data layer. That's really the heart of our value proposition. And then again, at the bottom, you've got the IT elements, network, virtualization type things. That's really what I like to call the connective tissue across the ecosystem. So if you think about what this looks like from an aerospace perspective, you've got at the top level, all of us that are interacting with this. So that could be the analysts, the engineers, software developers, decision makers, managers, anybody who needs to work within this ecosystem. So all of us. That second layer of the environment. Now we're talking about things like digital engineering workflows, model-based systems engineering tools, artificial intelligence, machine learning functions, all the collaboration tools, things that support software factory and development pipeline type things. In the data layer, we've got the actual ASOTs, the models, data sets that support all of this analysis, libraries. This is where we actually do in-depth data management and configuration management through techniques like metadata and tagging. And at the bottom layer, you've got all your networks, computation, storage, virtual machine type things. Now, really important to what's happening at Aerospace and is unique to our approach to implementing a digital engineering ecosystem is this idea of E3, you may have heard of. It stands for the Enterprise Engineering Ecosystem. And this is how most users are going to interact with the ecosystem, regardless of the layer, through catalogs that allow ready access to the data, models, tools, or software code, maybe a service catalog, customizable workflows that you can select and tailor. The intent for most users is to make the experience and the interaction with the ecosystem as transparent as possible. So users really don't know or care whether their services are coming from a public cloud, a private cloud. They get the services they need when they need it, and they can onboard onto this ecosystem in the most painless manner possible. So E3 is a key part of this. You'll hear about, they again provide the enabling services into this ecosystem and the overall platform to make it work. All right, let's move on to line of effort number 3. This is the authoritative data models and largely corresponds to that middle layer. That's really where it's focused, where we're talking about establishing standards for data and modeling. So when we talked about earlier in terms of the interoperability challenges related to being data-centric, well, part of that is ensuring we have mechanisms to effectively interoperate and communicate between different data sources. So there's a lot of standards work here in terms of data interfaces, ontology, establishing policy, governance, and best practices related to how we handle and manage that data. Also, we can think of data engineering as happening here in terms of the overall management strategies, curation of data, establishing and populating catalogs, again, exposing those to users that makes discovery and accessibility easy, and model portfolio management, all these different models, how they come together. And then data and model interoperability integration, got these ideas of how we translate and transform different services from different sources, the data engineering and architecture pieces. And, the example here would be these databases of blue and red, all of the systems that the Space Force manages or any other customer, the good guys, and then the bad guys, the red side. What are the threats? What do their architectures look like? And understanding and having a full inventory of those would certainly fit here as part of LOE number 3. LOE number 4, again, is capability development and modernization. This is defined as that broad portfolio of development and modernization projects. The heart of this is capability development and the mechanisms by which we more quickly and agilely deliver capabilities. It includes DevOps. It includes agile practices, and making those tools readily available to users as part of a more readily accessible workflow. Right now, the LOE4 team is working with Octo and various research leads to provide direction to various ATIP projects that are related to DE, support the selection of certain ventures activities, and in particular that involves ideas we've talked about to this point. Digital twins. What does a digital twin really look like, and what is the sustainable method for establishing and maintaining a digital twin across the life cycle? Also, digital sandboxes are a key part of LOE4 and really stretch across all the LOEs to some extent. And the idea of a place where you can learn and grow, and kind of a safe place in terms of different digital sandboxes, digital engineering, AI, ML, that kind of thing. M&S modernization support is also here in terms of coupling the DE initiatives to ensure that things are connecting, what pieces actually fit in a logical way with other things, identifying those connections and working through those. And DE transformation support in terms of customers. There's a lot of external engagement here. The ideas of model-based acquisition guidance, model-based mission assurance. Really, LOE4 is about developing all these capabilities and enabling all the processes, all the workflows that span the spectrum from really high TRL mature capabilities to really low maturity, and cultivating these across the company. There are actually, I believe, 6 pilots right now across all of ETG that are being worked. And then line of effort 5 is the people, the workforce education and culture. There are, to date, a lot of courses and training available to everyone across the company. That includes the Digital Fluency Digital Engineering Overview course. There's a link to the fully releasable version. Digital competencies and learning paths have been established where we dive deeper into these various categories of digital fluency. And there are right now 8 what we call introductory learning paths and 2 more advanced practitioner paths across these core competencies of digital engineering, data science, AI, ML, capability development, business processes, and modern infrastructure. And then we've established a bunch of learning resources tied to these things. There's the DE Learning Center. There's a DE guidebook that's in work, and I think at least a draft is out there right now that helps people reference, provide that ASOT for digital engineering capabilities and terms and concepts. And then there's a digital fluency site, glossary established. Again, these are all links to those sorts of things. And like I mentioned in LOE4, there's digital sandbox as well. To the extent that that's something that supports capability development, it's also supporting learning. And so I mention it here as well. And then workforce culture chain. And this is really the big challenge here. We're talking about a transformation in a lot of ways across the company, and it has a whole lot of technical pieces to it, but the culture is probably the biggest piece. I mentioned that in the challenges section. It's one thing to provide the capabilities and tools that enable a digital engineering approach to what we're doing, but it's another thing to get people to want to adopt that, incentivize them to do so, and make it clear that their lives are better, easier, can do things more efficiently by adopting these sorts of practices. So there's a lot going on here in terms of this course is certainly a part of just learning about digital engineering, but we're doing things more engaging, like road shows, expositions. In fact, the first one's coming up here in December of 2022, and those will continue indefinitely out to 2023 and 2024, certainly. All right. With the LOEs addressed, let's talk a little bit about the kind of overall transformation approach. And this is a pretty notional roadmap. It's not going to be a detailed schedule, but I wanted to show, relative to all these categories that we have been talking about as part of a digital transformation, the strategy of it, the governance, the resources, the people and culture, which is key, and meeting mission needs and the overall ecosystem and architecture. What are we doing relative to each of these like swim lanes or categories? Really, the DEIO is trying to take into account all of these challenges I mentioned earlier, and we're learning as we go, but these are the kind of things we're doing relative to each of these categories. There's the corporate vision that we've already established. There's DE strategy, there's M&S strategy. There's the idea of building out a capability framework of the things we need to do at the top level. And we're also working on transition strategy and business case kind of stuff as well. When you go down to like the governance layer, well, that includes things like standing up the right organization to do this, the DEIO, establishing leads for all of those lines of effort, building out charters, IPTs, and figuring out the structure for those and how these teams work together, getting all the research efforts aligned across digital engineering and M&S and connecting these in a way that is efficient for the company to pursue. And things like a data strategy. How exactly are we as a company managing our data from a strategic perspective? So these things all kind of get into governance, and in that case, a little bit of strategy too. Resources, those are increasing over time. More and more investments being put into this as we stand up and start making the transition. Maybe cost accounting is also something we need to think about here and as part of governance. What new methods for how to account for and allocate costs, both direct and indirect and program, non-program, in a world where you have a combined ecosystem that everybody benefits from, but investments are required across the board. Things are going to look a little different when you don't have your own set of servers within one particular portion of ETG that are just yours, but it's rather a part of a larger shared set of resources that are in the cloud that anybody can access on demand. That makes the cost accounting look different. In terms of people and culture, well, we talked about the Digital Fluency Initiative, the courses that are being established and have been established, various learning paths that you can focus on and dive into. This idea of a guidebook that's a good reference source, the expos I talked about in terms of outreach and engagement across the company. Mission needs is another area where we're really focused. This idea of, for instance, a stakeholder framework. What are the different user roles and functions that need to be supported as part of that larger capability consideration? What do we need to do from the perspective of user stories that establish mission threads and how those services are being provided in a certain way? We also are establishing a catalog for data and models, as well as for the tools. This could build up something called an app store where you readily access what you need, and from a self-service perspective, every user can access what tools that are most useful to them. Digital twins are certainly part of mission needs as we develop and establish that in a more operational sense. And maybe that migration handbook is kind of a combination of people, culture, and mission needs, helping people to onboard and migrate and adopt migrate into the digital engineering ecosystem. And then the ecosystem itself and the architecture related to that. We have digital test beds already established as part of what we've tried to grow and learn in terms of the architecture. We've already had an equivalent of like an IOC for our on-prem cloud, the unclassified level through E3. We're establishing ConOps for how data moves across these different platforms, in and out, how users interact with that and communicating that effectively. The sandboxes would probably be here, as well as the mission needs, maybe even into the people culture piece. We've established the initial services framework. What exact services are available at any given time, how you access those. So like essentially a storefront that users can go to get the kind of things they need, storage, compute, on into more complex things like establishing a software factory for development. These kind of things are part of the services framework. And then we're working a lot of pilots right now in terms of the off-prem commercial piece of this to learn and grow these capabilities rapidly. So that's kind of the overall roadmap of what we're doing. I'd say we're probably about halfway through this list of things, and there are probably a number of things we still need to capture going forward. But that should give you a general sense of what's happening across the board in terms of digital transformation at Aerospace right now. So in summary for this section, what is happening at Aerospace in terms of digital engineering? Clearly, the company is fully committed to digital transformation. They recognize the importance of doing this for not just the viability of our company, but just our ability to effectively support customers going forward, especially as they're on their own digital transformation paths. DIO, the Digital Engineering Integration Office, has been stood up. It's fully staffed. There are 5 separate lines of effort that are aimed at tackling the major parts of this challenge. And how does this affect you? Well, I would say, 1, take advantage of any additional learning opportunities that interest you. I've had a lot of references so up to this point of different places you can go. I'll have some more here in the last section in terms of additional references and courses. Certainly, if you regard yourself as a change agent early adopter, we'd love to work with you. Embrace that mentality. That's something that I think is a big part of the culture piece of this. Feel free to engage with the Digital Engineering Integration Office or representatives. I would be one of them. The overall lead for this effort is Dean Bucher, who is also the LOE1 lead. He's the Chief of Digital Engineering. You've got me as the lead for LOE2. That was the infrastructure environments ecosystem kind of stuff. Misak Zetland is the lead for LOE number 3. Richard Deakins for number 4, and Jennifer Smatt for number 5. So that takes us through the first 5 sections. We just completed what's happening at Aerospace in terms of digital engineering, answered what is the strategy, how is Aerospace implementing it. Let's just spend a few minutes here at the end to summarize everything and talk about maybe next steps, what other resources are available, and there's a little bit of reference in terms of the abbreviations and acronyms sort of thing. So section 6, the summary here. First, see a list of ways in which you can learn more about model-based systems engineering if you want to dive into that. You know, I talked about what it is, but certainly not to the practitioner level. A lot of these courses can get you there if you want to pursue that. To learn more about just overall modeling, languages, and frameworks, AU has a lot of great courses here. There are also some book references that were included that I actually pulled from part of this course. To learn more about cloud computing, there's another course you can take there. And then to learn more about E3, maybe the best place is just go to their website right now. I would also add, as these expos start getting deployed, and that's another great opportunity to engage, learn more about what's happening in D in general and E3 specifically. Data centrism, you can, the single best source here probably, especially for our community, is the DoD data strategy document. A lot of good content there. Other references in general, just that were used throughout the slide deck, are listed here. I won't walk through all those, but a lot of good sources. Same thing here, other references. There's more courses, there's websites, and again, just things that were referenced throughout the presentation. The other thing worth mentioning is kind of how this course fits into the larger set of digital fluency type related curriculum. And so this is a roadmap, at least the draft version. I think they're still working on to refine it more, but this should give you a good idea, the general landscape for digital fluency and how it relates. So we've got the Digital Fluency Overview course already established here, finishing up now the Digital Engineering Overview. Well, there's a lot of other stuff you can dive into here in terms of model-based systems engineering, in terms of the M&S, in terms of cloud computing, machine learning, agile software development, all these other course offerings that are great to dive into if you're interested to expand your learning further here. So a good way to close this out probably is to think about, did we meet the objectives that we set out at the beginning in terms of this course, what we wanted to do? Let me review these real quickly. You know, do you feel at this point you can identify and describe core components of model-based systems engineering, and how it differs from traditional systems engineering. So that progression from systems engineering to MBSE. But moving on to that with digital engineering, can you identify and describe those core components of digital engineering and really explain the difference between the two, recognizing that model-based systems engineering and digital engineering are distinct. They have a lot of common pieces, but they also have some differentiating features as well. Be able to list key benefits of model-based systems engineering and digital engineering. Be able to explain key concepts related to digital engineering, how they relate. That was the parts about digital thread, digital twin, ASOTs, the ecosystem, that sort of thing. Be able to cite specific examples of model-based systems engineering and DE. You may recall we walked through several examples, both aerospace and across the community, where parts of model-based systems engineering and DE are actually being accomplished today. We talked a lot about the challenges. There's a lot of promise with what digital engineering is, the fact that it could revolutionize so many aspects of engineering and capability development, but there are these challenges related to that. To be able to recognize those as well. Be able to summarize aerospace's approach to digital transformation. So we talked through the strategy, the vision, the establishment of the DEIO and the lines of effort. That's a big part of that. Be able to list and briefly explain the 5 lines of effort, and then be able to locate additional learning and reference sources. We just walked through some of that. So the closing part here, the just last few slides are purely referenced in terms of like these list of acronyms, initialisms, a couple pages of that. And that is the course. That concludes what we talked about today. I'd like to thank everybody for joining me in this and encourage you to continue to pursue learning across the board related to digital engineering and digital fluency. Thank you.